Hello everybody, a very warm welcome to Vedantu JEE English channel, and as I always say, Andariki Namaskaram, Ellargu Swagatam. This is me, your master teacher Nabamita Ma'am, and today we are going to start with this chapter called DNF block compounds, and we are going to end the chapter as well, like I always say. Yes, that means that this is going to be full chapter in one shot. So stick till the end of the session so that you understand the preparation of potassium dichromate, preparation of potassium permanganate, which I know that majority of the students you find it a little difficult. Otherwise, the chapter is going to be a little easy. Don't worry about it. So let's also take a look at what is the content, right? What exactly are we going to study in this chapter? In this chapter, as you can see, we are going to take a look at the introduction and classification of D block elements, that why are they called as D block elements. We will take a look at the physical and atomic properties of the D block elements. We will also understand what is electrode potential and chemical reactivity. And then we go to potassium permanganate, potassium dichromate, and finally the F block elements. Okay. Alright, so I hope that everybody is ready with a notebook and a pen as well. Also, please understand that this is where majority of the questions are being asked from. That is potassium permanganate and potassium dichromate. Most of the time in JEE mains, you will see that at least one of the equations, right? There are a lot of chemical equations if you have read the NCERT book. There are a lot of chemical equations from these two topics. And majority of the time in JEE mains or even in JEE advanced, you will see that they ask you questions from this part. Okay, all right, so let's get set go. What do you all say? What do you all say? Shall we start, everybody? Let us start. What do you all think? Yes, 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 yes. Quickly write down some la 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 in the chat box just so that I know that you all are ready with the session. Sure. Now, first things first, everybody, let us first take a look at the periodic table. What do you see in this periodic table? In this periodic table, obviously, you see all the blocks here, right? And I'm pretty sure that you all know that this side of the periodic block, this side of the periodic table, why am I saying block? No idea. Maybe I just woke up and look at me. I took a shower and tip-top babu ban ke aaya. I am like, pura, my mom would have been so proud of me. Anyway, coming back to it. So you see this side, this is your S block. Okay, what is this? This is your S block elements, right? And this side, this boron family, carbon family, nitrogen family, oxygen family, fluorine family, and the noble gases, they are called as your P block elements. I hope you know this, right? Now, what you might not know is that the S block and the P block, they are called as the representative elements. What are they called as? The representative elements or representative blocks of periodic table. That means that these are the OG blocks. These are the actual OG blocks of the whole periodic table. Are you getting my point? Yes. And what is it that falls in between these two representative blocks? You have the D block elements. Yes, what do you have? You have the D block elements. Now the D block elements, what is the speciality? They are also called as transition elements. You must have heard about it. What are they called as? They are also called as transition elements, isn't it? Transition elements. Now you might ask that why are they called as transition elements, right? Okay, so this S block and the P block, like I just told you, they are the representative blocks, right? They are the representative blocks. Now, these D block elements, what they do is, the properties from S block to P block, they change. And while they change, there is a transition that these elements bring about, and that's how they change. Getting my point? Yes. Why are they called as transition elements? Yes. And why not any other things? Yes. So the S block and the P block, they are the OG blocks of the periodic table. And the properties, when they change from S to P block, yes, they transition through this D block elements, and that's when they change. So these are called as your transition elements. Okay. The transition elements, they belong to group 3 to group 12, as you can see, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Okay. These are the groups that they belong to. Now you all know what are groups. Groups are top to bottom. Groups are top to bottom. Yes, groups are top to bottom. Right? And periods are left to right. Correct? Now, look at this. These ones, these fellows, they do not have a position in, actually they do not have a place in the periodic table. What we have done is we have pushed them and we have thrown them outside of the periodic table. This is outside of the periodic table only, right? They are called as what? Everybody knows it. They are called as F block elements. Yes. And these F block elements, if I tell you, there is a mind-blowing fact, everybody, that all of these elements, they all belong to one single group. Hey, how is it possible? Yes. How is it possible? Because these two, the lanthanum and the actinoids, yes, lanthanum and actinum, these two belong to group 3 and they are the leaders of this whole block. So when the leaders are only in the group 3, obviously the praja, what do you call it, the pawns, they are also going to be in the same group, right? So yes, my dear student, all of these, the 28 elements that you see here, they all belong to these group. That they all belong to group 3. Getting my point? This much is clear. This much is clear, okay? Now, in this periodic table, do you see that you have 1, 2, 3, 4? You have 3, 4. You have how many? You have 4 series. Do you see 4 series? This is 1, this is 2, this is 3 and this is 4. These 4 series, they have names. What are the names? The first one is called as, this first one that you see, scandium to zinc. This is called as 3D series. What is it called? This is called as 3D series. Okay, the first one is called as 3D series. All right, everybody. Yes. The second one, from yttrium to cadmium, this is called as 4D series. Okay. Then from lanthanum to mercury, it is called as 5D series. And actinum to copernicium, this is called as your 6D series. Okay. These are the series name. Now you might ask that, ma'am, but they don't belong to the third period. No, they belong to 1, 2. If I just count from hydrogen, see, hydrogen 1, lithium 2, sodium 3, potassium 4th. They belong to the 4th period. Then why are we calling them 3D series? It should be called as 4D series, right? Because D block and they belong to the 4th period. We must call them 4D series. Why do we call them 3D series? Well, you call them 3D series because the last electron, they fly and they go to the 3D orbital. That is why we call them 3D series. Now, tell me, why do we call the yttrium to cadmium group as 4D series? Because the last electron fly and go to the 4D orbital. Why is it 5D series? The last electron goes to the 5D orbital. 6D series, the last electron goes to the 6D orbital. That is why it is 3D, 4D, 5D and 6D. Okay. Now, what is the most concerning part of this whole thing that I have told you? In this whole story, the one thing that you have to learn is 2 things actually. Firstly, why are they called as transition elements? Because from the properties from S block to P block, they change and they transition through this block. That's why they are called as transition elements. First. Number second is, what is the one thing that you have to learn? You have to typically learn and keep it in your mind is the electronic configuration and atomic number of scandium to zinc, everybody. Okay, this is what you have to know. All right, now you're going to ask me that, ma'am, how do we remember it? Chalo, let me give you a trick. Okay, how do you remember it? You write down here Sachin Tendulkar. Okay, yes, Sachin Tendulkar, very crazy man, free coaching, Nick's cousin. I know. I've written the spelling of cousin wrong, but you get my point. Why have I written it? Now, what is our thing to do? What do we have to do? We have to write down that what is the name of the element that we're talking about. Sachin is scandium, SC, Tendulkar is titanium, Ti, vanadium is very, crazy is chromium, Mn is manganese, free is iron, coaching is cobalt, nickel is nick, and copper, and you have a zinc. All right, so where does the counting start from? The counting, everybody, starts from, take a look at it. Scandium is 21, Tendulkar is 22, vanadium is 23, chromium is 24, manganese is 25, iron is 26, cobalt is 27, nickel is 28, copper is 29, and zinc, my dear student, is 30. Alright everybody, is this clear? So now when I say scandium 21, titanium 22, vanadium 23, chromium, you have to say that it is 24. And like this you have to remember everybody. And every time somebody asks you what is the atomic number, count from the very beginning. Write it down. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. You keep repeating this, you will learn it. Okay. Now the atomic number you know, let me also write down the electronic configuration. It's going to be very easy. The moment somebody says that it is scandium, you know the atomic number is 21. Yes. Now what do you have to write? You have to write it is 3D14S2. For each one of them, you write down that 4S2 is common, 4S2 is common, not in case of chromium. 4S2 is common, 4S2 is common, 4S2 is common. 4S2 is common here, not in case of copper, and 4S2 is common. Now see how it changes, okay? Now see how it changes, everybody. Take a look at it. I'm also going to draw a line here so that you understand that where is the difference. Okay, this is where I have drawn a line. So these are the two types of, these are the two different rows of elements that we're talking about. So scandium, that is Sachin. Sachin is what? 3D1, 4S2. Tendulkar, titanium. Titanium is what? 3D2, 4S2. You got my point. Yes, you got the hang, everybody. Vanadium is 3D3, 4S2. Chromium, it is supposed to be 3D4, 4S1. 3D4, 4S2, right? But guess what? Have you heard of this term where we have said that the fully filled orbitals or the half filled orbitals are the most stable ones, and that is why instead of being 3D4, 4S2, what it actually is 3D5, 4S1. This is an exception, my dear student. Okay, this is an exception. Now, manganese is obviously 3D5, 4S2. Iron is 3D6, 4S2. Cobalt is 3D7, 4S2. Nickel is 3D8, 4S2. Copper, you got my point. You got my point. What is it going to be? Instead of being 3D9, 4S2, it will be what? It will be 3D10, 4S1, and finally zinc will be 3D10, 4S2. This is an exception, and chromium is an exception. As we move forward, I will tell you more about it. Okay, now coming to the point that what actually is the definition of transition elements, right? What actually is the definition of transition elements? Have we understood that? Have we figured that out, or still now we are still studying about that? Okay, no, let me tell you. The D block elements or the transition elements, they do have a definition, and the definition is very, very, very important. So please note it down, everyone. This is the definition that I'm writing, okay? The elements whose atoms are whose atoms or simple ions, yes, atoms or simple ions, everybody, whose atoms or simple ions contain partially filled d orbitals. Okay, partially filled d orbitals. Be very, very, very careful, everybody. What am I saying? I'm saying that the elements whose atoms or the simple ions, okay, the simple ions, that means even if one or two electrons goes away, they must have partially d orbitals. They must have partially filled d orbitals, and only then we are going to call them as what? Only then we are going to call them as transition elements. And if that is the case, my dear student, you have to understand that, now coming back to the periodic table here, you have to very well understand that. Take a look at it. Take a look at it, everybody. This zinc, cadmium and mercury. Do you see? Zinc, cadmium and mercury. Even as an atom, they have fully filled d orbitals. And as simple ions also, what happens is they still have fully filled d orbitals, which is why zinc, cadmium and mercury, they are not called as transition elements. Rather, what they are called as, they are called as pseudo transition elements. They are called as pseudo transition elements. Are you getting my point? Yes. What did I say just now? What did I say, everybody? I said that, yes, zinc, cadmium and mercury are pseudo transition element. Okay, pseudo transition elements. Now you will ask why? Because atom or the simple ions both have fully filled d orbitals. Okay, both have fully filled d orbitals, which is why they are not considered to be transition elements, but definitely they belong to the DNF block. They belong to D block, but they are not transition elements, my dear student. Are you getting my point? Is this much clear, everybody? So what are the things that we have learned? We have learned that S block and P block are the representative element. The properties, they change from S to P block and they transition through D block, which is why they are called as transition elements. The F block, they are called as inner transition element because they belong to group 3 of the D block, so they are inner transition elements. We also learnt the atomic number as well as the electronic configuration of the 3D series, which is the first series of the D block elements: scandium 21, titanium 22, vanadium 23, chromium 24, manganese 25, iron 26, cobalt 27, nickel 28, copper 29, zinc 30. We have learnt about this as well. Correct? Yes. Finally, we also learnt that zinc, cadmium and mercury, they are called as pseudo transition elements. They are not considered as transition element. Why? Because they have, even in their simplest ionic form or as an atom, they have fully filled d orbitals, which is why we don't call them as a transition element. And we know the definition of transition element. What is the definition of transition element? As an atom or as a simple ion, they should either have partially filled d orbitals or maybe 1-2 electrons in the d orbitals, but it should not be having completely filled d orbitals. Get my point? Is this understood, everybody? Great. All right. Yes. Now we come to electronic configuration, the general electronic configuration that we have to learn. Yes, let's learn about the general electronic configuration. The general electronic configuration, as my dear student, you can see right here, is that it is n-1 d1 to 10 ns1 to 2. Now you know that s orbitals have a capacity of holding on to just 2 electrons, right? Whereas d orbitals have a capacity of holding into 10 electrons. So it can be 1, it can be D1, D2, D3, D4, D5, D6, D7, D8, D9 and D10, which is what we have seen. Scandium D1, 3D1, 4s2. Titanium 3D2, 4s2. This is what you saw, right? This is what you saw. Acha, before we do this, let's also learn about the noble gas atomic number. I know that you probably do know about it, but I think it is my duty to just let you know all about it once again. So let me tell you that we all know that helium has an atomic number of 2, neon has an atomic number of 10, 2 plus 8. Here, see everybody, please note down, here is a very interesting fact that what are you adding here? 8. When you add 8, you are going to get 10, right? 2 plus 8 is 10. Now see, you are again going to add 8 here. You are again going to you're going to add 8 here and you will be getting 18, right? Which is the atomic number of argon, right? Now what you're going to do, check it out. Yes, 18 plus what are you adding now? 18 plus 18 is 36, isn't it? Okay, so the number has changed, everybody. The number has changed and this time you're going to add 18 and what will you get, my dear student? You will be getting 36, everybody. Okay. Now 36 plus 18, if you do, how much will you be getting? 36 plus 18, chalo, let's figure it out, everybody. 36 plus 18, okay, 36 plus 18, yes, you are going to get 54. Check it out. Are you getting it? Yes. 36 plus 18, if you do, how much will you be getting? You are going to get 54, everybody. Yes. And now 54 plus how much will you have to add? See, 54 plus 32, if we add, we will be getting 86, which is the atomic number of radon, everybody. What did I say? I forgot. Yes. This is what happens. Okay, here we have to add 32, everyone. Yes, what will you get? You will be getting 86, correct? Then after 86, once again, what do you add? After 86, once again, if you add 32, you will be getting 118, my dear students. Yes, which is the atomic number of OG, that is oganesson, the last element of the periodic table. All right. Yes. So what do you get, everyone? You get magic numbers. These are called as magic numbers, everybody. The magic number is 8, 8, 18. Actually, it is 2, 8, 8, 18, 18, 32, 32. So let me write that down. Yes, what is the magic number? The magic number is actually, how did I say that it is 2? Check it out here. Check it out here. Check it out. See, 1, hydrogen is 1. You do the same thing with S block elements. Do the same thing with S block element. You will see what you will get. Okay. See, hydrogen is 1. Yes, hydrogen is 1, everybody. Makes sense? Makes sense? Hydrogen is 1. Now, 1 plus 2 is going to give you what? 3. Right? 1 plus 2 is going to give you 3. Right? Now, 3 plus 8 if you do, how much will you get? 3 plus 8 if you do, check it out. 3 plus 8 if you do, you will be getting 11, which is nothing but sodium. Yes, 11 plus 8 if you do, check it out, everybody. 11 plus 8 if you do, yes, what do you get? 19, which is nothing but potassium, right? So what are the things that we have added? See, we have added 2 here, we have added 8 here, we have added 8 here. So twice 8, 8 is done. After doing 8, 8, now you have to add 18. Now you will have to add 18, okay? So 19 plus 18 if you do, how much will you get? 37, which is nothing but rubidium, correct? Yes, do you see? Do you see, everybody? Now 37 plus what will you add? 37 plus 18 if you add, you will be getting 55, which is nothing but cesium. Right? Yes. So do you see, everyone, what am I saying? Correct, everybody? Yes, 55 plus 32 if you do, what will you be getting? 55 plus 32. 55 plus 32, you will be getting 87, which is nothing but francium. Yes. So do you get my point? What is the magic number? The magic number, my dear student, is 2. Magic number, everybody, is 2, 8, 8. 18, 18, 32, 32. This is your magic number, and this way you can figure out, you can calculate the atomic number of any element. You just have to know that which one falls. So if you know just the beginning, if you just know the group of the elements, if you just know that which group it belongs to, which family it belongs to, you will easily be able to calculate. See, for example, I know that the atomic number of scandium is 21. So how will I calculate the atomic number of yttrium? See, it is 21 and then 39. That means what? I have to add 18. I have to add 18, and I know that scandium falls in the 4th block. So what is the 4th block? See, 8, 8, 18. The 4th period, sorry, not block, 4th period. What do I have to add? What do I have to add? 2 is done, 8 is done, 8 is done. I have to add 18 here. The moment I add 18, I get the atomic number of yttrium. Got it? So this is called as your magic numbers, and this is how you are going to calculate the atomic number of any element that is present in the periodic table very easily. This is one tip again for your JEE mains. Okay. Alright, now we go to the general electronic configuration, everybody. So take a look at it. As you know, what should be here in the first element, 3D series. What do we know? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and finally you should be having zinc. Okay, now do you understand why zinc's place was empty? That's because, as we know, zinc is actually a pseudo transition element. It's not a transition element for real, right? Yes. So what is the 3D series? What is their general electronic configuration? Their general electronic configuration is 4s 1 to 2, 3D 1 to 10. Okay, this is their general electronic configuration, and you see 3D is the last orbital, so that is why they are called as 3D series. Clear itna tak? Yes, everybody, are you all clear with this much what I have just taught you? Clear? All right. Let's move to the 4D series. The 4D series, what do we have? We have yttrium. Yes, changing the color. You have yttrium. Yes, after that, what do you have? Zirconium. You have niobium. You have molybdenum. You have technetium. You have ruthenium. Yes, ruthenium only, right? You have, yes, ruthenium. Alright, then you have rhodium. Alright, then you have palladium. Then you have silver, and finally you have cadmium. Alright, so what is the electronic configuration here? The electronic configuration here is 5s 1 to 2, 4d 1 to 10. Cool. Alright, Now we go to 5D series, my dear students. And 5D series, what do we have in 5D series? We have obviously the first one is lanthanum, then you have hafnium, then you have tantalum, then you have tungsten, then you have rhenium, you have osmium, then you have iridium, then you have platinum, gold, and mercury. Okay. In this case, what is the electronic configuration? By now you have figured it out. It is going to be 6s 1 to 2 and 5d 1 to 10. Finally, we come to 6d series. The 6d series, what do we have? We have actinium here. Yes. Then we have RF, that is rutherfordium, everybody. Yes, you see rutherfordium, 104 is rutherfordium. All right. Then what do you have here? You have dubnium, you have db. All right, then you have sg, then you have bh only, right? Yes, borium, then you have hassium. All right, then you have hs, then you have mt master teacher, no. What is mt is meltnerium. Okay. All right, I believe so. I'm not very sure of this name. Nobody has to learn this. Okay. Then you have ds, then you have rg, and finally you have copernicium. All right, so these are your 6d series. So by now we are done with 4d, 5d, 6d, and 3d as well. 3d though, obviously. Correct, everybody? Yes, are we all clear with this much? Are we all clear with this much? But now, exceptions. It's chemistry. Yeah, mystery though obviously will be there, right? Without mystery, how can we learn chemistry? So once again, I'm going to write down all the elements, and this time we will see that there are certain elements which you see. Do you see that I have colored it with brown? And we're going to understand that what actually happens in this case. Okay, what actually happens in this case? Let's understand. Sure, let me write that down. Okay. All right. As I was telling you, look at this. Yeah. So we are going to start writing all the elements here, and you will see that which one of these have exceptional electronic configuration. Now I'm going to talk about the whole DNM block. I've already told you that copper and chromium in the first series, that is 3D series, they are exceptional because they have 4s1 3d5 or 4s1 3d10, right? So let's take a look at all of them. Now I'll tell you all about all the exceptional electronic configuration. Yes. So what do we have here? We are going to write scandium here. We are going to write titanium here, vanadium here, chromium here, manganese here, iron, cobalt, nickel, copper, and zinc here, right? Yes. Now coming to the next series, not gonna waste too much time because you already know yttrium here, zirconium here, niobium, molybdenum, technetium, Ru here, then you have rhodium here, palladium here, then you have silver here, and cadmium here. Okay. All right. Then coming to the next series, you have La here and you have Ac here, which we obviously know. Right. I hope that you are all able to see it. If you're not able to see it, don't worry. I will just move right here so that you can see the whole page. Okay. All right. Yes. Then what do you have here? You have hafnium, tantalum, tungsten. Yes. Rhenium, osmium. Yes, then you have iridium, then you have platinum, then you have silver, and then finally you have mercury here. Okay. And then here we have RF, then we have DB, then we have SG, then what do we have? What do we have? We have borium. Yes, we have BH, then we have HS, then we have MT, then we have DS, and then we have RG, and finally we have CM. All right. Yes. Now you will see that how all of these guys, they have different electronic configuration. They do not follow the usual convention of electronic configuration, but their electronic configurations are exceptions. They are almost equal in number to the normal ones, right? Yeah, this is what happens in D block. Anyway, so check it out, everybody. For chromium, what do we write? For chromium, we write 4s1 3d5. Okay. All right. For copper, we write 4s1 3d10. All right. Yes. Then we come to niobium, everybody. Niobium is 5s1 4d4. Okay. Then we have 5s1 4d5 for molybdenum. Now technetium, please listen to me very carefully. Technetium, if you go and search it on Google, you will find two kinds of electronic configuration that people are talking about. Okay, in your NCRT, it is given to you as 5s1 4d6. However, if you read JD Lee, which I have, and if you read other inorganic chemistry books, yes, the most popular inorganic chemistry books, that you will find that technetium also is said to possess 5s2 4d5, which does make more sense because 5s2 is fully filled, 4d5 is half filled, and we know that the fully filled fully filled orbitals and the half filled orbitals are supposed to be more stable. So this does make more sense. But by chance, they will not ask in JEE mains. They usually do not ask you such confusing such confusing electronic configuration. But if they ask, by chance if they ask, you will follow NCERT. This is just good to know, everybody. This is good to know that technetium, according to JD Lee, the book of inorganic chemistry, the Bible of inorganic chemistry, it says that it is supposed to be 5s to 4d5, which does make more sense because half-filled and fully filled stability both are seen in this electronic configuration. However, in your NCERT, and if you look into Google, you will find that in many places it is given as 5s1 4d6. But because it is in there in your NCERT, please follow these. By chance in JEE mains they ask this question, you will write down 5s1 4d6. No challenging there. You will write down what NCERT has. Got my point, everybody? Yes. Now don't say which one is wrong, which one is right. We are going to follow what is there in NCERT. However, like I said, in JD Lee 5s2 4d5 is written, which makes more sense because half filled and fully filled stability both are here. Got my point? So for technetium, now I know you are going to ask me, but ma'am, what if it comes in JEE mains? Follow NCERT. They will also follow NCERT and they will give you marks according to NCERT. So please know this, okay? All right. Now we have ruthenium. So it will be again 5s1 4d7. Okay, for rhodium it is going to be 5s1 4d8. Everybody, do you see? Now palladium is actually very different from everybody. Okay, it is absolutely different from everyone. So palladium has 5s0, yes, and 4d10. This is again the very different, absolutely different from all of these. Okay, 5s0 4d10, which we do not see in any other element, everybody. Okay, then we have silver, which is again 5s1. Sorry, not writing with this this color, otherwise you will think that all of them are different. So coming back to the green color that we have 5s1 4d10. Okay, then we come to lanthanum has lanthanum has here 5p6 is also there, 5p6, 5d1 and 6s2. Okay, all right. Yes. Now we come to platinum. What is platinum? Platinum has 6s1, 5d9 and 4f14, guys. Do you see what is happening to platinum? Yes. Now 4f entry has also happened. Okay, all right. Then we go to gold. What does gold have? Gold has, of course, 5d10, 6s2. No, 6s1. 6s1. Gold has 6s1. 6s1, 5d10. Okay, all right. Then we come to actinium. Actinium has 4f14, 6d1 and 7s2, my dear student. And finally Rg has again 5f14, 6d9 and 7s2. These exceptions you must remember. Out of this, you always have to remember technetium and palladium. Palladium is different. Now you might ask that, ma'am, why palladium is not a pseudo transition element, although we see that 4d10 it also has fully filled. But what was the definition? The definition was that simple atom or simple ion, the atom or the simple ions are supposed to have partially filled. Now if palladium is there, if I do palladium plus 1, palladium plus 1 will have 49, right? Plus 2 will have 48. See, half filled, partially filled has come across. We have come across partially filled. That means that palladium cannot be pseudo transition element. Yes, clear, everybody? This much is clear. We should not have taken so much time, but it's okay. We're teaching for the first time, right? We're learning this chapter for the first time. So I hope that this much is clear. Once this much is clear, now shall we solve a question? Let's solve the question, everybody. So the question is, in which of the following pairs the outermost electronic configuration will be the same? Check it out. In which of the following pairs the outermost electronic configuration will be the same? Will it be Ni2 plus and Cu plus? Will it be Fe2 plus and Co plus? Will it be Cr plus and Mn2 plus, or will it be V2 plus and Cr plus? Let's take a look at it, everybody. Yes, let's try to solve it. Now we know that. Okay, I'm going to move this side. Now we know that Ni, what is the atomic number for Ni? Ni is 28, right? 28. Now it is saying that Ni plus 2. Ni plus 2 means it will be 3d8, just 3d8, right? Now we solve for Cu plus. Cu plus, we know that it is 29. So that means that Cu plus will be having 29 bole to 3d10 4s1. So even if we take one electron, it will still be 3d10. So this is not the answer. That means option A is definitely not the answer. Next one, everybody, is Fe plus 2 and Co plus. Fe, what is Fe? Fe is 26. So 26, that means 3d6 4s2 plus 2 means 3d6. Yes, and cobalt has 27. 27 means 3d7 4s2 plus cobalt in plus oxidation state. That means it will be what? 3d7 4s1. This is also wrong. This is also not the answer, right? Then we come to the third one. Third one is Cr plus and Mn2 plus. Cr has an electronic configuration of 3d5 4s1. 3d5 4s1. So if you take away one electron, it will be 3d5, everybody, right? 3d5. Mn2 plus. Mn has 3d5 4s2 2 plus. If you take away, then this will also be 3d5. So yes, we got our answer. That is option C, everybody. Option C is the correct answer. Makes sense, everybody? Yes, makes sense. Check it out. Check it out if you are finding any other answer. But I think this should be the correct answer. This was very easy. And guess what? This has come in JEE Mains 2021. Can you believe it? Such an easy question. You see how you're going to get 4 marks absolutely free of cost, everybody. Do you see? Yes, option C is the correct answer. Moving on to the next question, everybody. The next question is the positive oxidation state for an element with atomic number 24. Who has atomic number 24? Atomic number 24 is obviously chromium. Chromium is atomic number 24. Now chromium, what is the electronic configuration for chromium? It is 3d5 4s1, right? 3d5 4s1. So what it will do is, now the most common oxidation state, please know this, this is something that I'm telling you, we will read about it. The most common oxidation state for each of this 3D series, okay, most common oxidation state is +2. So obviously it will show +2. But apart from that, you see that it can take away 1 electron from here, 2 electron from here, so it will also show +3. Yes, it will also show +3. You can take 1 electron from here and you can take 3 electrons from here. That means that +4 can also be seen. You can take 1 electron from here, 4 electrons from here. That means that +5 is also possible. And you can take away all 1 and 5. Everything you can take away. That means +6 also it will show. So that means that +2 to +6, everything it will show, and that means that option A is our correct answer. We will be reading about oxidation state as well, don't worry. But right now, is this question clear to you all? Is this question clear to you all, everybody? Yes? +2 to +6, option A is our correct answer. Got it? Chalo. Now, shall we move on to the next topic? Yeah, the next topic is, everybody, melting and boiling point. Now that you are clear with the fact that how many electrons they have in the outermost shell. Okay, before we move forward to melting and boiling point, do you understand this? Whenever we are writing the electronic configuration, did you see that we are always writing the D as well as the S? We are always writing 3d5 4s1. We are always writing 3d10 4s1, right? We are always writing 4s2 3d1, 4s2 3d3, 4s2 3d4, right? Why are we writing both 4s as well as 3d? Have you thought about it? Let me tell you another mind-blowing fact. So basically, when you draw an electron, when you draw an atom, what do you have? You have the nucleus here, right? And then you have electrons here like this. Electrons are here rotating or just existing, right? The cloud is there. Now, when we go to 1s, then we have 2s, then we have 2p, then we have 3s, then we have 3p, right? All of these have a different energy level. But did you know that this 3d, the 4s, the energy gap between these levels is so small, that the ultimate shell, let's call the ultimate shell, if the ultimate shell is 3D, 4s is not too far away. 4s will be like, but I'm also here only, let me also participate. So 4s also wants to participate. So if the 3D is called as the ultimate shell, it's called as the ultimate shell, everybody. 4s will be called as the penultimate shell. Okay. So the ultimate shell and the penultimate shell, the difference in the energy gap is so small that everybody wants to participate. For example, let me tell you a story. You have a class of 40 students, let's say. In your school, you have a 40 students ka class, right? Yes, all the 40 students are there. Now, let's say that you are the topper. You are the topper. And how much marks do you get? You get, let's say that 99 point you got, let's say in chemistry, you got 99.5. Okay. But there is the second topper. The second topper in the class has 99.4. The energy gap, the gap between the marks is so small that next unit test or the next test that you have, in that what happens is this one becomes the topper and you become the second topper. So you see how both of you are participating to be the topper. Like the moment you must have just not done, one silly mistake you must have made in the units, and that is why the second topper became the topper. So you see, the competition is too strong. Both of you want to participate. Both of you want to contribute towards being the topper. You are understanding? The same thing, this is what the ultimate shell and the penultimate shell does. The moment the ultimate shell is like, oh, electrons are coming up, it's my time, it's my turn to participate, the penultimate shell, I'm also right here only. Bro, what do you want to participate? I'm also right here. I will also participate. So both of them contribute towards forming a bond. Both of them contribute in the reactions. Yes, do you understand, everybody? You guys are understanding, I hope. All right. So now coming to the point of melting point and boiling point, do you see that both 4s and 3D are the shells who are contributing? Yes. Now in case of group 1 and group 2 elements, the S block elements, we know that group 1, the whole group has what oxidation state? Group 1. Group 2, beryllium, magnesium, calcium, strontium, everybody has what is the oxidation state? 2. Right. But here you get to see variable oxidation state. We will talk about that also. Don't worry. Yes. We will be talking about that as well. But now, the group 1 and the group 2 elements that we know about, the S block elements, right? They are, when you call them metal, that feeling does not come to call them metal, right? I mean, look at sodium, bro. I mean, what a poor metal it is. You can take a knife and you can slice it down. Who expected that metals will be so soft? We don't expect our metals to be so soft, right? We want metals like iron, something that even like, if we want to break it, we will have to be incredible Hulk to be able to break it. And sodium, look at it. Take a knife and slice it. You can take your hands and you can like just do this and sodium will melt. A worst metal that is, right? Worst metal. We don't want to consider that as a metal. But here, you see iron, you see manganese, you see copper. Do you understand why they are so strong? Because hey, 4s and 3D, all of them are trying to have a metallic bonding with each other. Hence, the bonding is so strong. And now, if you look at the graph, you will see that actually, as the number of unpaired electrons are increasing, the melting point, the metallic bonding is also increasing, hence the melting point increases. Yes. Now look at the graph, everybody. Look at the graph. See, scandium will be somewhere here. Scandium, titanium, vanadium, chromium. Chromium has the highest. Why, you are going to ask me? Why? Okay, tell me something. Did you see here? Chromium has 1 plus 5, 6 unpaired electrons, Baba. There are 6 unpaired electrons, and all the 6 unpaired electrons, they will be like, let's donate it to the CEO of the positive ions that we have. Let's all form bonds. Let's all stay together. Yes, the metallic bonding is very strong here. The metallic bonding is very strong here, which is why we see that chromium has the highest melting point. Now, there is another trend that you will get to see in this curve. Do you see that as you go down, right? What do you write? You write chromium. Then what do you have just beyond chromium? Okay, take a look at this place. Take a look at this page. After chromium, you have molybdenum. After molybdenum, you have tungsten. So do you see now? Now look at the graph, everybody. Now look at the graph. See, chromium, molybdenum, tungsten. Do you see that tungsten has the highest melting point, which is why it is used in the bulb? Yes. Why? We have noticed that out of 3D, 4D and 5D, the heavier metals will have higher melting point. Yes, what did I say? The heavier metals will have higher melting point. Heavier metals will have higher MP and BP. Alright. Why? Why? Because bigger size, more metallic bonding. Yes, bigger size. The electrons are free. The electrons will form bonds better, and that is why they will have higher. Now, look at the graph very nicely. Do you see that here, in case of manganese, in case of technetium, and in case of rhenium, there is a drop. There is a drop in the graph. Why so? Why so? Because after chromium, now what happened is manganese has one less unpaired electron and there is a sudden drop. Okay, manganese has how many? 3d5, 4s2 is paired, right? 4s2 is paired, 3d5 is unpaired, so there is a drop. And same thing with technetium as well as rhenium, everybody. Right, everyone? Technetium, did you remember? 3d5. So in case of manganese, what happens is the half filled stability also is a factor. Half filled stability, everybody. Yes, half filled, 3d5 half filled stability as well as the fully filled stability, that is 4s2 3d5, they're very stable, so they want to stay as it is. They're like, why bond and all, Baba? 3d5 I have half filled stability, I don't want to bond, I'm fine. They will stay like this. And same thing you will also get to see after Ag, when there comes zinc, you will see that zinc also is a brittle metal. Zinc is not a very strong metal. Do you remember that? You must have heard it somewhere, you must have read it somewhere, even in your younger classes you must have read it, that zinc is a brittle metal. Zinc is not a very strong metal. Why? Everything is fully filled. Everything is fully filled. 4s2 3d10, 4s is also fully filled, 3d is also fully filled. Even after losing 2 electrons, 3d10 still fully filled. No electrons are, no electrons are very excited to form bonds. They are like, we're fine only. It's very nice, yeah. Less people will like it like this. yeah, so that's why we see that the melting point drops. That's why we see that the melting point increases in case of chromium, molybdenum and tungsten. Why? Because more number of unpaired electrons. Okay, all right. So what did I say, everybody? Let me write that down. Involvement of greater number of electrons from n-1d in addition to ns electrons in the interatomic metallic bonding. Yes, and that is why, because of stronger interatomic bonding, transition elements have high melting and boiling point. So let's write that down. What did I say? Involvement of greater number of electrons from where? n-1d and ns electrons, right? Ns electrons in the interatomic metallic bonding. Okay, because of stronger interatomic bonding, transition elements have high melting and boiling point. Okay, because of stronger, writing it down so that you will have the whole PDF with you. I'll be providing this in the Telegram channel. If you haven't joined, please do join it so that you get all the notes, everybody. Yes, because of stronger interatomic bonding, transition elements have high MP and BP. Yes, it increases, everybody. All right, it increases. Cool, everybody. Yes, are you all understanding? Now, by chance, if somebody asks you, okay, that which group has the highest melting point, you know it, everybody. Check it out. Chromium, molybdenum, tungsten, all of them belong to the same group, isn't it? What is the group? They belong to the Third is scandium, titanium, vanadium, chromium. So third, fourth, fifth, sixth group has the highest melting point. Now from here we come to another term called as enthalpy of atomization. If you look at the name of this topic, you will understand that what we mean. What do we mean here? Enthalpy of atomization. Chalo, let me write down the definition first so that you understand it a little better, okay? Let me write down the definition here. I think that, no need to look at the graph. Don't look at the graph now. Just look at the definition, what I'm writing, okay? The enthalpy of atomization is the enthalpy change that accompanies the total separation of all atoms in a chemical substance. For example, if you have a chemical substance, let's just say that you have CH4. Yes. Now, CH4 is a molecule. From here, if you want to separate all the atoms, atomization, from a molecule, you are making atom. And to make that atom, how much energy do you have to provide? The energy that you are providing to separate each atom, that is your enthalpy of atomization. Let's just write it in a beautiful English way so that everybody can get 2 marks in your boards, right? If by chance they are. This may come in the board. Obviously, in J means nobody asks you about definition. So just good to know. Okay, good to know. So the enthalpy of atomization, beautiful English, which might sound very confusing, but you know what is enthalpy of atomization. All right. The enthalpy of atomization is the enthalpy change enthalpy change as in energy change that accompanies the total separation of all atoms in a chemical substance. All right, yes. Now the more extensive an element is, metallic bonding will be more. Yes, and the atomization of enthalpy would be more. So that means that we can once again see that chromium, molybdenum and tungsten, they have higher enthalpy of atomization. Yes, they have higher enthalpy of atomization. Do you see here? Higher enthalpy of atomization. Why? More electrons that are unpaired and more electrons that can form extensive metallic bonding. So higher enthalpy of atomization they have. And once again, everybody, do you look at it that manganese will have a drop in enthalpy of atomization because the number of unpaired electrons have reduced. Zinc will have the least enthalpy of atomization, which is once again, everybody, coming back to it. Zinc is a brittle metal because it lacks these unpaired electrons. So writing that down as well for you, everybody. Yes, zinc has lowest enthalpy of atomization, everyone. Yes, zinc has lowest enthalpy of atomization because it lacks the unpaired electrons. Yes, it does not have the unpaired electrons. Yes, so basically you can always understand that, yeah, zinc is the exception here most of the cases. However, there is another exception, by the way. Just behind chromium, what do you have? Scandium, titanium, vanadium, chromium. Chromium also has a very high heat of atomization among the 3D series. Yes, sorry, not chromium. Vanadium also has a very high atomization. Now for this we don't have any reason, but it just has. Okay, it just is like this, that yes, vanadium also has a very high heat of atomization. Why so? Maybe because it is just increasing. What does it have? It has 4s2 and 3d4, right? 3d3 4s2. So I think these 3 unpaired electrons, they are very strong. But I mean, it's just like a, no need to understand, just know that this is also an exception, that vanadium also has one of the highest heat of atomization. Cool, everybody? All right, now we come to the fact. Once again, let me try to just make you just explaining this in a different way. See, for chromium, we understand that how many electrons do we have, everyone? Chromium has 3d5, isn't it? 1, 2, 3, 4, 5 and 4s1. See, all of them are unpaired. So that means that altogether you have 6 unpaired electrons. 6 unpaired electron. I'm just writing here UE so that you understand, everybody. Let's write UP E. Okay, unpaired electron. Look at molybdenum. What does molybdenum have? Molybdenum also has 1, 2, 3, 4 and 5 and 6. See, 6 unpaired electrons, same thing. Yes, tungsten also has, see, tungsten will have 1, 2, 3, 4 and 5 and 6. Yes, do you see that this also has 6 unpaired electrons? So that means the more number of unpaired electrons, what happens? More is the metallic bonding and more is the enthalpy of atomization. So that means that chromium, molybdenum and tungsten will have the maximum unpaired electron. That is why they are very hard metal. Whereas zinc, cadmium, mercury, they have no unpaired electron, which is why they are brittle metal, right? They are what? They are brittle. This is something that we know from a very young class, isn't it? They are brittle. They are not very hard metal. Cool, everybody, is this clear? Any doubts here? I hope that everybody has understood. From today, you will fall in love with DNA block, guys. So easy, so simple. Because every time you look at the question, you will be actually able to solve the question and you will be like, wow, I love this chapter. Same happened to me also. Same happened to me also. Now we come to another topic, that is atomic radius. That means that we want to know that how does the atomic radius change. Now, talking about periodic properties. From the periodic properties chapter, we know that atomic radius, as you go from left to right, what happens? We expect the atomic radius to decrease. Why? Because Z effective increases. What is Z effective? Z effective is basically the effective nuclear charge. What is effective nuclear charge? You have an atom. At the atom center mein you have the nucleus. The nucleus has the protons. The protons are positively charged particles, right? Once again, everyone, what is Z effective? Let's understand this very well. Okay, let's understand this very well. Just like the male teachers, I have seen K.R. Abhishek sir and everybody doing this. Now even I have come to that this thing. I have also come, I am also in that position where I just have to take a look at my hair again and again and see if it is looking fine, because hey, it's growing and I want to grow it. It's in that weird phase. Enough of my hair problem. Come back. So in periodic table, when we look at the periodic table, right, we know that as you go from left to right, we expect the atomic radius to decrease. We know that group 1 elements have the highest atomic radius, and as you keep going this side, what happens? We expect it to reduce, right? Except obviously the noble gases. We leave the noble gases because they have hardly any bonding or anything, so they want to stay away from each other, and they also have really huge sizes, right? We know that. So that means that when we are moving left to right in a 3D series, what do we expect? We would expect that obviously the atomic size is reducing, but that does not happen. That does not happen. Okay. In a periodic table, when we say, in general, we say that in the periodic table from left to right, what happens? The atomic radius decreases. Do you know why? Because as I just said, that if this is an atom, in the atom right here at the center you have the nucleus. The nucleus has neutrons and protons. Neutrons are neutral, right? They don't have any charge. Protons are the positively charged. And hey, we know that the electrons that are revolving around, they have negative charge. So the positive charge will obviously try to attract the electrons which are negatively charged, right? Now, if there are more number of positive charge, that means the more will be the attraction. They will be able to hold on to the electrons very well, right? Which is why when you move from left to right, the atomic number increases. Atomic number increases. That means protons are also increasing. The number of protons are increasing. Number of protons increases. What happens? Effective nuclear charge. Yes, the positive charge of the atom increases. And if that increases, then what is happening? Obviously, the atomic size will reduce. But this is something that we don't get to see here. Why? So Z effective is increasing, but with that being said, there is also another factor that works here, and that is the electron repulsion. Yes. So when you try to push, okay, understand this here. So if this is the atom, everybody, this is the atom, this is the nucleus here. So you have electrons here, you have electrons here, and you have electron here as well. Now what happens is, these electrons, they try to repel the outermost electron and the size increases. Alright, and the size increases. So basically there are two factors that work here. Yes, the moment you see that the atomic radius is increasing, what is the reason? Electron repulsion. The moment you say that the size is decreasing, that means what? The number of electrons, number of d electron has increased. That means Z effective has increased. Z effective increases, atomic size reduces, and electron repulsion increases. The atomic size increases. What? No, I said the same thing. Wait. Z effective increases, atomic size reduces. Electron repulsion increases, the atomic size also increases. So atomic size basically depends on two things, that is nuclear charge and the electron repulsion, everybody. Alright, so what do we see? We see that from scandium to chromium, the size decreases. Why? Alright, let's write it down, everybody. From scandium, right here, this is your scandium. From scandium to chromium, you see that there is a decrease in the size. Why? Why? I just told you. Z effective has increased. Yes, because Z effective is increasing, the size is decreasing. Right? Now what happens? You see that from manganese to nickel, yes, from manganese to nickel, you will see that the size is nearly constant. Why? This time what happens is the Z effective and the electron repulsion, they are compensating each other. They are almost equal. So Z effective wants to reduce the size, whereas electron wants to increase the size, and which is why they almost remain constant. Now when you go from copper to zinc, do you see that there is an increase? Why? This time what is happening? This time the electron repulsion has increased, my dear students. So I hope that you all are clear with why, why don't we see that there is a constant decrease in the size as we move from left to right? Because of, two factors. Like I said, that atomic radii, it depends on two things. That is, number one is, okay, not this color, yes. Number one is what? Number one is Z effective charge, and the second part is the electron repulsion. Okay, the electron repulsion. Yeah, electrons are basically, how they say, you are humanity, how we say for humankind also, that man is the ultimate enemy of mankind. Exactly, the electron himself or herself, the electron itself is another electron's enemy, as well as friends also. You see how they repel? You see how they repel? Yeah, that's what happens. All right. Yes, that is what is happening here. So I hope that atomic radii, the trend of atomic radii is absolutely clear to you, my dear student. Yes, let's move ahead then. Now we will understand something called as trends in standard electrode potential. Now this might be just a little difficult for you, so please try and understand. Okay, don't look at the trend now. Don't look at the trend. Also, even if you look at this graph, do you see any trend? There is no trend actually. It's very irregular, isn't it? It is very, very, very irregular. Now, do you know why? Okay, let's explain this, everybody, and after that you can take a break. Okay, after that you can take a break. Chalo. So let's understand. What is the standard electrode potential? Now, in the standard electrode potential, please take a look. What is it? What is written here? Do you see what is written here? M2 plus 2M. M2 plus 2M. Now, M2 plus is the ion and M is obviously the solid metal form. So that means that my equation, right? My equation for this M2 plus 2M must be somewhat like this. If you look at it, it will be M2 plus, yes, M2 plus aqueous form, right? Plus, I will have to take 2 electron. It will have to grab 2 electron to become M in the solid form, right? That is exact reaction that is supposed to happen. That is the exact reaction that is supposed to happen. But do you really think that it is as simple as just grabbing 2 electrons and getting to the solid form? No. And to understand standard electrode potential, what we are going to do is we are going to write exactly the opposite of it. Okay. Now it's time for us to understand. So what we're going to do is we're going to write exactly the opposite of it. So what did I write? I wrote M2 plus, right? M2 plus, which is in the aqueous state, it is going to grab hold of 2 electrons and it is going to form M solid, right? But that's not what I'm going to write now. What I'm going to write is, I'm going to write exactly the opposite of it, just so that we understand this concept better. So M solid form is supposed to be M2 plus, yes, aqueous, and it is supposed to lose 2 electrons, right? Correct, everybody? Now, do you think that the opposite reaction that I have written is this simple? Is this very simple? No, of course not. Nothing in chemistry is very simple. Now, for me to be able to convert it to M2 plus, there are several steps that I will require. My first step will be from solid form, I'll have to take it to an isolated gaseous form because I have to take away 2 electrons, right? I have to take it to an isolated gaseous form. So what will I do? For me to be able to take it to gaseous form, what do I have to provide? I have to provide here sublimation energy, guys. What do I have to provide? Oops. Where is it? This is 16. This is 15. Where did the... Okay. Let's write it down here again, okay? So it is M2 plus aqueous plus 2 electron will be forming M in solid form, right? Yes. But what did I do? I took the opposite of it. Solid form will be forming M2 plus aqueous, and obviously it will be losing 2 electron. Correct? This is what is the reaction that is supposed to happen, and only we are writing this to understand the standard electrode potential. You know, you can read this in NCERT, but it will sound a little confusing. So please listen very carefully. Pay attention. First thing that I have to do is I will have to provide it here. I will have to provide it sublimation energy. Okay, what do I have to provide? Sublimation energy so that I can take it to the gaseous form, right? Okay. Once I take it to the gaseous form, now what do I have to do? Now I have to take it to the M2 plus state. Yes. And even now it is in gaseous form. It is still in the gaseous form, but I have to take away 2 electrons. How do I take away 2 electrons? I will have to provide ionization energy 1 plus I will have to provide ionization energy 2, my dear student. And when I do that, when I do this, okay, then what happens? I have the metal in 2 plus ion, right? Now from here it will get converted to aqueous form. How? When it releases delta H hydration. So that means that when we say that there is a standard electrode potential, yes, when we talk about standard electrode potential, my dear students, do you see that there are 3 energies that are working here? What are the 3 energies? The energies are delta H sublimation energy, then you have ionization energy, and then you have delta H hydration energy. There are 3 energies that are working here to take the electron, to take the metal to its solid state or to take it to the aqueous state. Are you understanding? Is this clear, everybody? It's such a long process. And because of this long process, what do you have? You get the standard electrode potential. Now the standard electrode potential, if you look at it carefully, you will see that there is no regular trend. Why? Because the D block elements actually do not have a regular ionization energy trend or sublimation energy trend. That means due to the irregularity of the ionization energy and the sublimation energy, the transition elements also have irregular standard electrode potential. Are you understanding? So let me write that down here. What am I saying? I'm saying that due to irregular ionization energy and sublimation energy trends, the standard electrode potential is also irregular. You get my point? Yes, everybody? Yes. Now, do you see that copper here has a positive? Everybody, take a look at it. Copper here has a positive standard electrode potential, whereas the rest, all of them, minus 1.63, minus 1.18, minus 0.9, minus 1.18, minus, everything is negative. Copper here has a positive standard electrode potential. So remember, I said that there are 3 things that are working here. What are those? Sublimation energy, ionization energy 1, ionization energy 2, and then hydration energy. And please make a note here. The sublimation energy and the ionization energy is something that you provide to the atom, right? But hydration energy is something that the atom releases, okay? They release hydration energy, and that's how they attract the water molecules. So everybody, why does copper have a positive standard electrode potential? Because the ionization energy and the sublimation energy is so much. You are providing such high ionization energy and sublimation energy that the hydration enthalpy is not able to compensate. That the hydration enthalpy is not able to compensate, which is why copper has a high tendency to get converted to solid form. And do you remember this from electrochemistry, everybody? That copper was what? Copper was gaining electron is reduction. Copper was readily available to go to the reduced form. Do you remember? It was grabbing hold of two electrons and forming copper solid and getting deposited in the cathode. Red cat, reduction was happening in the cathode. Exactly my point, everybody. So let's write it down. So what did I say? I said that the ionization energy and the sublimation energy is so much that the hydration enthalpy, yes, is not able to compensate, okay, is not able to compensate. This can be asked in your board exam, definitely, okay? And there are questions regarding JEE mains also here. Yes, I will tell you that, okay? Compensate. So Cu has high tendency to do what? To get converted to M solid. It wants to get converted to its solid form, everybody, okay? It always wants to get converted to its solid form. All right, everybody. Yes. Now, if you look at now, let's take a look at another term here. That is, now we are going to take a look at M3 plus to M2. Okay, that means that if you take away three electrons and then if you try to push one electron, yes, M2 plus, that means only 2 electrons are lost, and 3 plus means 3 electrons are lost. What is the trend here? In this case, everybody, you will see that, okay, so titanium is here, but if you see that scandium will be even lower, okay? Scandium will be somewhere here. Scandium has the lowest E naught. Yes, what did I say? I will write it here again, everybody. Sc3 plus, that is scandium 3 plus to Sc2 plus is lowest. Why? Why? Because remember, scandium has an atomic number of what, everybody? Scandium has an atomic number of 21. That means that it is 3d14s2. Yes, if it loses 2 electrons, it will only have 3d1. And that 3d1 is unstable. It would readily want to give away the electron. It's like, please take it away. So you see that when Sc comes to 3 plus state, it is very stable. It comes to 3d04s0, which is why Sc3 plus is more stable, and that is why it has the lowest E naught value. Okay. All right. Yes. Now here cobalt is given. You will see that zinc. Okay. If this trend was continued for a little while, here I'm writing it down, everybody, just so that you know. Zn3 plus to Zn2 plus is highest. Zn3 plus to Zn2 plus is highest. Once again, my dear student, what can be the reason? We all know that zinc is atomic number 30. That means that it is 3d10 4s2. Zinc at 2 plus state is very stable. Yes, it becomes 3d10 4s0. If you want to take away another electron from the fully filled d orbital, it would not want to give away, right? It will not want to give away from this 3d10. So we understand that Zn2 plus is stable. It is highly stable. That is why Zn3 plus to Zn2 plus will have a highest E naught value. Okay. All right. Now from this graph, there are two more things. There are two things, I think. Two more things, everybody. Now if you look at Mn also has a very high E naught value. Same thing, bacha. Do you remember that Mn2 plus, the moment you write Mn2 plus, that means that it will come to the 3d5. 3d5 is half fill stability, isn't it? 3d5 is half filled stability, but choose. Yes, half filled stability will have, it will be like, no, don't take over my other electron, right? Yes, half fill stability configuration, which is why it is not gonna give away the third electron. It will be like, no, 2 close is fine. No, why do you want to take the other electron, right? It will not want to give away. Now coming to iron. See, iron has a drop. Fe has a drop. Do you see why? Do you see why? Why does it have a low E naught value? Why does it have a low E naught value? Because everybody, take a look at it. Yes, iron here, that Fe plus 2. Fe plus 2 will have what configuration? It will have 3d6 configuration. But Fe plus 3 will have a configuration of 3d5, which is once again half filled stability. My dear students, so half filled stability will be better for iron. That is why Fe3 plus is more stable and it readily gives away one electron to attain half filled stability. Alright, everybody, got it, guys? Got it? Now coming to the point again, the electrode potential of M2 plus 2 M of 3D element, they show positive values for copper. Why? Because ionization energy and sublimation energy is so much that the hydration energy cannot compensate. Okay, please do make a note of it. Please do make a note of it. It is very important. It has come many times in the exam. So just make sure that you know every fact regarding this chapter. Alright, everybody, now shall we solve a question here? Chalo, let's solve a question. The question is, the electrode potential of M2 plus 2M of 3D series elements show positive values of, as you know, the answer is copper. Why is the answer copper? Because as we know that the ionization energy and the sublimation energy, provided is much more than hydration enthalpy released by the atom. So it wants to stay in the solid form, that is its reduced form. Got it clear, everybody? Yes, I hope you know that ionization energy is something that you have to provide. I have told you this in periodic properties. If you haven't watched the video, please go back to the channel. You will find periodic properties, electrochemistry, coordination compound part 1 and part 2. You will find mole concept and stoichiometry, chemical bonding, you will find structure of atom. All of these chapters are already covered, my dear student. Please go back and watch this if you haven't. Chemical bonding and periodic properties and coordination compounds are basics of this chapter. And vice versa, D and F block is again the fundamentals of coordination compound. It's like a prerequisite. It's like a vicious cycle. So you have to do these chapters. All right. Please don't delay it anymore. Now, moving on. Let's go to the next question, everybody. The next question is, the E naught value of Ce4 plus to Ce3 plus is plus 1.74 volt. Okay. Yes, plus 1.74 volt. Ce is more stable in Ce plus 4 state than Ce plus 3 state. What do you think? Is this right? What do you think, guys? Is this right, everybody? Think about it. Think about it. Let me move on, actually. Let me just move out of the frame so that you can study this, study the question and find out the answer. Go, check it out. Check it out, everybody. Yes? What do you think? Actually, let me tell you, everyone. No. Ce plus 3. Okay, this is from the, this is not from here that we're talking about. This is from F block, okay? Yes. Now you have to understand that Ce plus 3 is actually the most stable oxidation state, okay? It's the most stable oxidation state of lanthanide series. Yes, it comes to the F block, but you will be learning about it, don't worry, of lanthanide series elements, okay? Yes, and lanthanide series, they have the most common oxidation state as plus 3. Just like how D block elements and D block elements have plus 2 as the most common oxidation state, the F block has plus 3 as the most common state. So that means that the statement 2 is wrong, but statement 1 is right. So that means that statement 1 is correct, but statement 2 is incorrect. So option B is the correct answer. Just like I said, option B is the correct answer. Got it, everybody? Is this clear? And now we are going to go to oxidation state. Chalo. So when we talk about oxidation state, right? First of all, actually take a look at this whole table. Yeah. What do you see here? What do you see here? You are seeing variable oxidation state, right? Now, again, once again, coming back to the S block, the group 1 and the group 2 elements. If you look at the group 1 and the group 2 elements, you will always see that the group 1 elements, everybody, right? Talking about lithium, sodium, potassium, rubidium, cesium, everybody has only one oxidation state because they can only let go of one electron. Then when you come to group 2 elements, you will see that everybody throughout the group, beryllium, magnesium, calcium, strontium, everybody, they have only two oxidation state, right? Yes, that means they can only let go of two electrons. I mean, two electrons can participate and form bonds, correct? Yes, but that's not the case here. Here, you will get to see plus 2, plus 3, plus 4, plus 5, plus 6, plus 7 oxidation state. Why such variable oxidation state? Why such variable oxidation state? Now, if you remember, once again, coming back to the point that I told you, right? What did I say? The ultimate shell and the penultimate shell, that is Ns and N minus 1d, the energy levels, the gap between the energies are so small that both the orbitals, the ultimate shell and the penultimate shell, the electrons that are present in these orbitals, both of them wants to participate. And that is why we get to see variable oxidation state, my dear students. So let's just write that down. Yes, what did I say? I said that in case of oxidation state of D elements, right, you will see variable or variation of oxidation state. Let me write down here, variable oxidation state. Variable oxidation state. And what is the reason to it? What is the reason of variable oxidation state? I just told you that due to similar energies, of Ns and N minus 1 d orbitals, okay, N minus 1 d orbitals of electrons, both can participate, yes, both can participate to show variation in oxidation state. Cool, everybody? Do you all understand? Yes. Now, what is the most common oxidation state? Once again, take a look at this. Yes. The most common oxidation state, you can see that titanium exists in +2. Vanadium exists in +2. Yes, you can see that CrO, chromium also exists in +2. Manganese exists in +2. Everybody, all of them are existing in +2 except scandium. Scandium does not show +2 because scandium, when it loses the 4s2, there is only one electron in 3d, and that way it is not able to stabilize itself. It readily wants to give away the 3d, that one electron is present in 3d. It just wants to give it away so that it can attain stability. So scandium is the only one that shows +3 oxidation state, whereas rest all of them show +2 oxidation state. So everybody be very careful that this is the most common oxidation state, okay? The most common oxidation state is +2. Get it? Get it? Get it? And what is the highest oxidation state? The highest oxidation state, my dear student, as you can see, is obviously Mn. Manganese exists +7 oxidation state. Manganese exhibits +7 oxidation state. All right? Yes. Apart from that, in case of the whole D block, Ru and OS, okay, Ru and OS bole to let's just 1 second, let's just go back to the just a second, yeah, just a second. Let me show you here that where is Ru and OS. We have written a lot, isn't it? We have see Ru and OS, this ruthenium and osmium. Ruthenium and osmium, okay, yes, everybody, ruthenium and osmium, if you can see, can you see here, right here, these two, they show +8 oxidation state, which is the highest, okay? They show +8 oxidation state, which is the highest among the whole DNF block. Got it, everybody? Is this clear? All right, is this clear, everyone? Understood? Great. Okay, once again, let me just write it down here as well, just so that you all understand. Ru and OS show +8 oxidation state, which is the highest, okay? Now the heavy elements in D block, right, they are more stable at higher oxidation state. You will see that they are more stable in higher oxidation state. For example, what am I speaking actually? See, Cr exists in +6, right? Cr, chromium exists in +6. But apart from, although chromium is showing a +6 oxidation state, even then the elements or the metals that are below chromium, that is molybdenum and tungsten, when they show +6 oxidation state, that will be more stable. So what did I say here? What did I say? That molybdenum 6 and tungsten in 6 oxidation state will be more stable. Okay, these two will be more stable. They will be stabler than chromium 6. Okay, all right. Yes, everybody. Now coming to the fact that these oxides, these are the oxides that they all exist. Correct? Everyone can see it, right? Apart from this, there is also something called as mixed oxides. Okay, there is also something called as mixed oxides, which you can see right here, everybody. Do you see that Mn3O4, Fe3O4, CO3O4, these are mixed oxides. What are they? These are mixed oxides. So for example, Fe3O4, how do you write it? You write it as Fe2O3 and FeO2, right? No, FeO, yes, just FeO. Just FeO will give you, yes, dot FeO. So Fe2O3 dot FeO. This is a mixed oxide. That means that both the types of oxide, that is Fe+2 and Fe+3, both of them will exist together. And the same way for Mn3O4, the same way for CO3O4 as well. Okay. All right, everybody. Yes. All right, got it, everybody? So this is about the oxidation state. Now, so there were a lot of students when we were doing, remember when we were doing a question regarding amphoteric oxide, basic oxides and acidic oxide, many students were asking me a lot of doubts. So guess what? Metals not only exist as basic oxide. This is something that we have read in our junior grades, that metallic oxides are always basic oxide. That's not the case. That's not the case. Okay, so let me write it down and explain it to you here, that metals can show, you know, here, yes, metals can show basic oxides, metals can show amphoteric oxides, and metals can also show acidic oxides. All right, they can also show acidic oxides, my dear students. So who all can show basic oxides? When the metal is in +1 or +2 or +3 oxidation state, that's when they show basic oxides. So that means that if you look at it, all of these, everybody, check it out, everybody. TiO, VO, CRO, MNO, FeO, COO, NiO, CuO, ZNO, Ti2O3, Sc2O3, Mn2O3, Fe2O3. These are all what? These are all, everybody, basic oxides. Okay, what are these? These are all basic oxides, everybody. Okay, all of these are basic oxides. Now, moving on. Who is going to show amphoteric oxides, everybody? The +4 oxidation state is always, most of the time, not always. We never say always, yeah. Let's forget about this word called always. Always is not a word, not a word in our dictionary when we are chemist, okay? Yes, +4 is amphoteric oxide. So that means that +4, everybody. Where do you see +4, everyone? Where do you see +4, everybody? Yeah, do we see +4? Where do we see +4? We can see it here. TiO2, V2O4, CrO2, MnO2. These are all +4 oxidation state. And what did I tell you just now? +4 oxidation state is going to be amphoteric. Okay, this is going to be amphoteric. Now, finally, you're going to ask me, so ma'am, who shows acidic oxides? Bachos, my bachos, everybody. Please make a note of it. Yes, the +5 oxidation state, the +6 oxidation state and +7 oxidation state is always going to be acidic oxide. So that means that the lower oxidation states are basic, the middle oxidation state, the intermediate oxidation state is amphoteric, and finally the higher oxidation state is going to be acidic. Is this clear? Is this clear? So which ones are acidic oxide then? Which ones are acidic oxide? Everybody, V2O5. V2O5 is also amphoteric, but it has a more acidic character than basic character. I will write that down, don't worry about it. CrO3, where it is existing in +6, it is acidic oxide. Mn2O7 is also an acidic oxide. Cool, everybody? But let me write that down here very carefully. Please do make a note of it, everyone, that V2O5, okay? V2O5 is amphoteric, but yes, V2O5 is amphoteric with more acidic character than basic, okay? With more acidic character than basic. Cool hai, everybody? Are you all clear with this? Are you all clear with this? Cool, everyone understood? Yes. So the highest oxidation number is achieved by manganese +7. Just making a note of it, everybody, whatever we have just now studied. The lower oxidation states are basic in nature, the intermediate ones are amphoteric, and the higher ones are acidic in nature. Mn2O7, CrO2 here, CrO3 and V2O5. V2O5 is amphoteric, it's an exception, just make a note of it. V2O5 is an exception, it is amphoteric, but it does have a more acidic character. So what is happening? When you are moving from bottom to top, everyone, right? When you are moving from bottom to top, you see that you are increasing the acidic character slowly and steadily. It was basic, right? It was basic here. From basic, you are adding acidic character, then it became amphoteric. Amphoteric bole to, it can react with acids as well as it can react with bases, right? And then you keep adding more acidic character, it becomes completely acid. It becomes completely acidic, all right? Yes, so this was the whole thing about this particular series. Apart from this, let me also tell you that which ones, other than this, which ones are amphoteric oxides. Other than this, some more amphoteric oxides that you must know is, everybody, please take a look at it. Arsenic, As+3, Fe+3, Sb+3, Cr+3, vanadium +5 and tellurium +4. These are all of them are amphoteric oxide. Yes, apart from that, what else? Write it down. Zinc, obviously, Sn, Be, Al, Pb, gallium and cadmium, these all also follow amphoteric oxide. Make a note of it, it is very important. Later on when we solve question, you are again going to ask me, ma'am, which ones are amphoteric oxide? So make a note of it, everybody. These are the ones that will form amphoteric oxide. Now we go and understand the trends and stability of higher oxidation state, but we are going to talk about halides, everybody. What are we going to do? We are going to talk about halides. So chalo, let's talk about it. So if you look at the table, yes, by any chance are you able to gather anything? Are you able to understand anything from this table? Yeah. But if I point it out to you, you will be like, oh, this is what is happening, ma'am. Let me point it out. Let me make your life easier. Yes. Okay, everybody. Do you see here that titanium here, TiX4, yes? The highest oxidation numbers are achieved. It is a tetrahalide. Obviously, you can see that X4. There are 4 halides. What is X? X is basically a halogen. X can be fluorine, chlorine, bromine, iodine, all of that, right? So TiX4 here, okay, TiX4 right here, everybody, it's a tetrahalide and the highest oxidation number is achieved at +4, okay. All right, then you see that VF5 and CrF6, okay. All right, so right here you can see that vanadium achieves the highest oxidation state at +5 with fluorine, and Cr also attains +6 oxidation state but with fluorine. All right. However, in the previous in the previous this part, right here you saw that Mn, manganese, can also exhibit +7 oxidation state, but right here, do you see that? You don't see that. Why is that so? Actually, this is written in your NCERT book that just Mn cannot show +7 oxidation state with a simple halide, okay? MnF4 is the only thing that you will be able to see. So let me write it down here, everybody. Please point, note it, everybody. Yes, the +7 oxidation state that you usually see with manganese, yes, the +7 oxidation state for Mn is not seen. or Mn is it's not represented. That's what is written in your NCRT, is not seen in simple halide. Yes, it is not seen in simple halide, but you do get to see it, but you get to see it in MnO3F. In MnO3F, you will get to see the +7 oxidation state. Okay, all right. And beyond manganese, if you look at it very carefully, you will see that beyond manganese, the metal, the beyond manganese, no other metal will show you trihalide, except till cobalt you will be able to see it. Iron and cobalt, they do show trihalides, but after that you will not get to see trihalide as well. Now you might be asking that, ma'am, all the higher oxidation states that you get to see with the halides, it's always fluorine. Why why is that so? Chalo, let's write that down. Let's write that down. In fact, let's write it as a question. Okay, let's write it as a question. Does that work to you? Yes, does that work for everybody? Chalo, let's write it as a question. The question is, why fluorine exists with higher oxidation state? Why only fluorine exists? Why only fluorine exists with higher oxidation states? OS means oxidation states. Huh? After so much of teaching, I'm lazy to write now, please. Okay, so let's write down the answer, guys. What is the answer, everybody? Answer is the ability of fluorine to stabilize the higher oxidation state is because there are two reasons. Number one is that higher lattice energy. Yes, higher lattice energy in case of you see COF3. Yes, all right. Or there is a possibility that you get to see higher bond enthalpy. What do you see? Higher bond enthalpy. That means that you require more energy to break the bond. Okay, so higher bond enthalpy in terms of covalent compounds, right? For example, VF5 and CRF6, right? In these cases, you will see that these are covalent compounds. Both of these are covalent compounds, my dear students, okay? Both of these are covalent compounds, everybody. And in this case, you will see that they have a higher bond enthalpy. So these are the two reasons why fluorine exists with higher oxidation state. So my dear student, if this is asked in your board exam, you will still be able to answer. See, I'm teaching you not only for board, but for JEE Advanced as well, everybody. Do you see it? Yes. Okay. All right. Now moving back to it. Do you also see that CU X2 or X3? Right here there is another exception, and the exception is that Cu plus 2 oxidation state. Yes, plus 2 oxidation state halides are known. Yes, halides are known. But you will never find it with iodine. You will never find it with iodine. You will find all the other halogens with copper at plus 2 oxidation state, but not with iodine. Why is that so? Chalo, let's write that down as well. Let's write that down. Changing the pen color so that you know that this is another term. Okay. So let me write this down. Again, this is also there in your NCRT book, but just letting you all know that all Cu2 halides, okay, copper at plus 2 oxidation state, halides are known, except you would have never heard of copper with iodide, okay, except the iodide. Why is that so? That's because Cu2 plus, what it does is Cu2 plus, it oxidizes. I will move away from the frame just a second. Yes, oxidizes I minus to I2, which is why there is no way you can find copper 2 plus halide. Yes, copper 2 plus halide, but which halide I'm talking about? Iodide. You will find halides. You will find fluorides, copper fluoride, copper bromide, copper chloride. You will find, but copper iodide you will not find. Why? Because look at this. Look at this reaction. 2Cu2 plus if you take 4I minus, what it will form is, it will give you Cu2I2. Yes, copper oxidizes the I minus to I2, and that's how you get a solid state of this, and plus iodine. All right. Yes, everybody, getting my point, everybody? Got it? Clear? Is this clear? All right. Now we are going to solve a question. We are going to solve a question. But apart from that, what other thing do we have to speak about? Is there anything else that I'm leaving? Oxidation, number of metal increases, ionic character increases, and do you know that? Do you know that if the oxidation number of a metal increases, then the ionic character decreases? Okay, this is another exception that you have to talk about, that you have to know. So let me just write it down here if I can. I don't think I can. Anywhere else can I write? I can write it here. Okay, so let me write it down here. Yes, as the oxidation number, as the oxidation number of a metal, that means that when you see manganese is at +7 oxidation state, right, what will happen? Fion's rule. It will be small cation but more charge. If there is more charge, that means what will happen? Covalent character will increase. Covalent character will increase. So that means that right here what you see, Mn2O7, this is a covalent molecule. This is a covalent molecule. I left this when I was teaching you higher oxidation state. So let me just write that down. As the oxidation number of metal increases, yes, what do we see? We see that ionic character decreases. Okay, ionic character will decrease. Ionic character will decrease. Cool hai? Cool hai? Yes. All right, everybody. Okay. All right. Now, apart from this, now let's solve a question. Everybody ready to solve a question? Yes, we are done with oxidation state also. Yes, now we are almost there and we are reaching towards F block. But before that, we will be solving an amazingly important topic, that is potassium permanganate and potassium dichromate, for which we will have to be a little, before which we will have to have a little bit of patience, because yeah, many reactions, and I know you don't like reaction, but trust me, after today you will like reactions as well. Yes, because we are going to make it so simple and super easy. So the nature of oxides V2O3 and CrO is indexed as X and Y type respectively, and the correct set of X and Y is, I think everybody knows that in case of V2O3, right, in case of V2O3, what do you see here? You see that vanadium is in what state? Vanadium will be in +3 oxidation state, isn't it? +3 oxidation state. If you don't believe me, you can check it out. See, V2O3, everybody, where is V2O3? V2O3 will be here. V2O3. Yes, V2O3 will be here, and V2O3 has a +3 oxidation state, right? Next one, what is given to us? Next that is given to us is CrO. Check it out, everybody. Yes, where is CrO? CrO is here, where the Cr is in +2 oxidation state, okay? Cr is in +2 oxidation state. So both of them are at the lower oxidation state. And what did I tell you? I have given you this notes also, everybody. +1, +2 and +3, all of them are basic oxides. So that means that option D makes sense to us, everybody, right? X is basic, Y is also basic. Correct, everyone? Yes, does this make sense? Does this make sense to you? I hope that you all are clear with it. Amazing. All right, let's go to the next question. Woohoo, we are right. Check it out. We are right. Yes. Moving on to the next question, everyone. The next question. Oh, we don't have a next question. Now we are going to talk about, what are we going to talk about? We are going to talk about the magnetic moment, everybody. Okay, what are we going to talk about? Magnetic moment. Now, N is equal to the number of, how do you calculate magnetic moment? When I was teaching you coordination compound and I told you that this is how you calculate magnetic moment, many students asked me that, Mom, I still cannot understand that what are you doing with this formula? So let's talk about it. To find out magnetic moment, this formula is used, okay, where mu is basically the magnetic moment. What is mu? Mu, this is your magnetic moment, is equal to root over n multiplied with n plus 2, where n is what? N is the number of unpaired electrons, okay? N is the number of unpaired electron. Do you see it? N is the number of unpaired electron. Now, the magnetic moment in units of, so once you get the result, whatever number you get here, the unit of that is B capital M capital. That means that it is Bohr magneton. What is it? Bohr magneton. Okay, so mu is calculated in terms of Bohr magneton. Now, everybody, what do we know? Look at this. Sc3 plus. Sc3 plus. What is the atomic number of scandium? Atomic number of scandium is 21, right? If it is 21, that means it will be 3D14S2. Now I am saying here that scandium is in 3 plus oxidation state, everybody. If it is 3 plus oxidation state, that means it is 3D04S0, and that means the number of unpaired electrons right here is 0, everybody, which means that now if I calculate it, if I put 0 here and then 0 plus 2 here, 0 plus 2, that is 2 multiplied with 0 is 0, root over of 0 is also 0. So what is the calculated Bohr magneton? 0. Make sense? Make sense, everybody? Understanding? Now look at it. Titanium 3 plus. Okay, titanium 3 plus will have 1 electron. Number of unpaired electron is 1. What is the calculated Bohr magneton? Check it out here. 1 multiplied with 1 plus 2, that means 3. Root over 3 is the answer. Now for root over 3, if I calculate it, everybody, let's calculate, everyone. You will see what you find out. You will see what you find out. If you don't believe me, and then I will tell you. Yes, the answer is 1.723 or 732. Okay, 1.732. That is the correct answer. Now check it out. Ni2 plus. Okay, Ni2 plus. Then the configuration becomes 3D8. And for 3D8, I will have to draw the orbitals here. Check it out. What am I doing? 1, 2, 3, 4, 5, right? D orbitals. There are 5 D orbitals, correct? So that means that 1, 2, 3, 4, 5 and 6 and 7 and 8. Okay, so that means there are 2 unpaired electrons. Now put it in this formula. What is the formula? Formula will be 2 plus 2 root over. How will you calculate? 2 plus 2 is 4, 4 2s are 8. So root over 8 becomes how much? Root over 8 becomes, everybody, chalo, let's calculate that. Also, where do I have? Root over 8. Yes, 2.82, everyone. Yes, what is it? 2.82 is the calculated Bohr magneton. Now let's go to vanadium 2 plus. Vanadium 2 plus has electronic configuration of 3D3. That means there are 3 unpaired electrons. For 3 unpaired electrons, I will have to calculate like this. 3 plus 2, that means 5, and 5 into 3 is 15. So root over 15 will be how much, everybody? Let's calculate once again. Root over 15, everybody. Root over 15, calculate. What do you get? 3.87. 3.87. Okay. Then you have Cr2 plus. Cr2 plus has a electronic configuration of 3D4. That means there are 4 unpaired electrons. Now put it, everybody. Yes, once again, what do you get? What do you get? 4. 4 plus 2. 4 plus 2 is 6. 6 4s are 24. So root over 24. What will you get? 4.89. Yes. Mn2 plus 3D5. That means there are 5 unpaired electrons and 5 into, okay, let's do it again, everybody, here. Yes, 5 plus 2, 5 plus 2 is 7, 7 into 5 is 35, so root over 35 will be giving you 5.91. Now, do you see a trend here, everybody? Do you see a trend here? If there is 1 unpaired electron, then the value comes to be 1.73. If there are 2 unpaired electrons, the value comes to be 2.82. If there are 3 unpaired electrons, 3 point something. 4 unpaired electron, 4 point something. 5 unpaired electron, 5 point something. And that means that we have come to a trick here, and the trick is that how much ever unpaired electron are there, majority of the time you will see that the magnetic moment in Bohr magneton will be 0.75 to 0.83 more than the number of unpaired electron. What did I say? What did I say, everybody? Writing it down just so that you understand. The calculated Bohr magneton, the calculated magnetic moment, okay, calculated magnetic moment in terms of Bohr magneton or BM, okay, or BM, Bohr magneton is generally observed to be 0.75 to 0.83 more than the number of unpaired electrons. You get my point, everybody? More than the unpaired electron. Yes, do you all see it? Do you all see it, what I said? Yes? Okay? Alright, chalo. Okay. So here we have come to the end of magnetic properties. We're done with magnetic properties as well. Now, can we take a look at a question? Let's calculate one of the questions here, everybody. Okay. The spin only magnetic moment for magnetic moment in Bohr magneton for free Ti3 plus, V2 plus and Sc3 plus ions respectively are, hey guys, I have just told you, Ti3 plus, okay, titanium. See, check it out. Titanium has a atomic number of 22. 22 means 3d24s2, and Ti3 plus means that it will have 3d1. If it is 3d1, that the calculated Bohr magneton will be 1.73 or something. Yes. If it is vanadium, vanadium has an atomic number of 23. That means that 3d3 and 4s2, that means that if it is V2 plus, that means that 3d3, that means that the Bohr magneton calculated will be 3 point something something. Yes, let's just say 75. Okay, I'm not even calculating, I'm just trying to show you that how you can do it very fast. Scandium 3 plus, scandium has an atomic number of 21. That means that scandium 3 plus will be having 3d04s 0, and that means that the Bohr magneton will be 0. That means that what is it that we are getting at? What is it that we are getting at? We are getting option B, I think 1.73, 3.87, and option B. Yes, option B is the correct answer. Well done, everybody. Well done. Let's read the next question, everybody, and let's try to solve it. Chalo. The question says, what is the spin-only magnetic moment value of a divalent metal ion with atomic number 25 in its aqueous solution? Okay. When we say divalent, what do we mean, bachus? Any idea? What do we mean by divalent? Yes. Any idea what we are talking about? And the atomic number is 25, by the way. Okay. So atomic number 25 is obviously Mn. Correct. Yes. Scandium, titanium, vanadium, chromium, manganese. Manganese is 25. Right. So manganese is 25 and it is a divalent metal atom. That means I think they are talking about Mn plus 2. Mn plus 2 will be normally it will be 3d5 4s2, correct? That means that Mn plus 2 will be only 3d5, and if it is 5, then what can be the magnetic moment? It has to be somewhere around option B, 5.92. See, calculated and easy peasy, everybody, right in front of you. See, got it. All right, next question. In the ground state of atomic Fe, that is iron is Z is equal to 26. Everybody knows atomic number is 26. The spin only magnetic moment is, okay, be very careful. It's nothing very complicated, by the way, huh? It's just written 10 to the power minus 1. Okay, so first of all, let's calculate the Bohr magneton. Okay, so we know that Fe, what is the electronic configuration of Fe, or just the last one will also do. It will be 3d6 4s2. Am I right? Yes. So the number of unpaired electrons. So the number of unpaired electrons are here. Number of unpaired electrons will be in the ground state. 3d6, right? 3d6. So if I draw it like this, it will be 1, 2, 3, 4 and 5. So 1, 2, 3, 4, 5 and 6. So that means 4. So number of unpaired electrons are 4 here. Correct? Yes. So let's calculate then. What do we have to do? Mu is equal to 4. 4 plus 2. Yes, like this. That means 4 plus 2, 6. 6 into 4 is 24. Root over 24 would be, root over 24 will be equal to 4.89 around. Yes. 4.89, that means it is 4.9. Correct. Now 4.9, instead of writing it as 4.9, can I not write it as 49 into 10 to the power minus 1 Bohr magneton? I can write it. So that means your answer is 49. That means that your answer is 49, everybody. Check it out. Yes, I hope that I'm clear. Yes, everybody is clear with it. Great. Yeah, they see the answer is 49, everyone. Answer is 49. Moving on to the next question. The next question is the oxide that shows a magnetic property is. The oxide that shows magnetic property. Just by looking at it, I know the answer. The answer is Mn3O4. Mn3O4 does show magnetic property. Now what you can do is you can calculate for all of these. Okay, just calculate for all of these and find out that why is it Mn3O4. Let me give it to you as homework. Yes, calculate for all of them. and figure it out that why only Mn3O4 has magnetic properties and why not the others. Will you all do that? Will you all do that? Yeah, I really hope so you do that. I really hope that you do that. Chal. Moving on from here, now we have to talk about the colored compounds. Okay. Yes, so how do we talk about the colored compounds and why do they show colored compounds? I mean, we know that D and F block elements, yes, they show colored compounds because we also know, my dear students, that do you remember in coordination compound that majority of them were actually D and F block that showed the colored compounds? Do you remember that, everybody? Yeah or no? Do you remember? In coordination compound, we spoke about them largely, isn't it? We kept talking about that, yes, most of the metals were from the D block elements. And they showed a color. Why? There were two things. There were two things. Do you remember? One was DD transition and the other one was charge transfer. So we are going to talk about that. Specifically, we know that when light of certain frequency falls on the complex, or not even complex, let's just, yeah, colored compounds, right? We are talking about colored compounds. So what happens is when light of certain frequency falls on the complex, it does absorb light from the visible region. Yes, from the visible region they absorb light, and for the transition of electron from lower D energy level to the higher D energy level, what happens? They exhibit colors. They exhibit color. Alright. Now when the color that they showed, it also dependent on nature of the ligand. These are all the things that we have studied in coordination compound, my dear student. Yes. We have studied about all of these in coordination compound. So I'm just giving you a quick recap of it, okay? Just giving you a quick recap of it. So we know that it dependent on nature of ligand. If the ligand was a weak field ligand, then the splitting was less. The color was of a lower energy. If the ligand was strong field ligand, the splitting was more. So what happened was the absorption of the wavelength was of shorter wavelength, were absorbed because shorter wavelength have higher energy, right? It also dependent on geometry of complex. It also dependent on presence of unpaired electron. Yes. So that means that if you look at it, everybody, yeah, we will see that D1, D2, D3, D4, D5, yes, D6, D7, D8, D9, wherever there is even a single unpaired electron. Even if there exists a single unpaired electron, you will get to see color. But in cases like D0 or D10, where there are no unpaired electron or no electron at all, then obviously you will not be getting to see any color, right? Yes. So the observed color is always complementary of the color that is absorbed. And what do we mean by that? For that, we will have to draw the color wheel. There is a color wheel, okay? So how do we draw the color wheel? The color wheel, for you to be able to draw it, you draw a circle like this. Then you halve it like this, and then keep it. Now, how many colors do we know? Vibgya, right? Violet, indigo, blue, green, yellow, orange, red. Instead of writing all of them, let's write violet, blue, green, yellow, orange, and red. So if violet is absorbed, then yellow will be shown. If blue is absorbed, then red will be shown. If orange is absorbed, then green will be exhibited. Are you understanding? Whatever is absorbed, the complementary color is always visible. Is this clear? Is this clear, everybody? Now, what we see is, I was just telling you that there is either it happens because of DD transition, either it happens because of DD transition. Yes, now you might ask me that, ma'am, what is DD transition? Chalo, let me show you that also. For example, let's say that these are the 5 orbitals of D. Okay, this is D orbitals, 1, 2, 3, 4 and 5, right? 1, 2, 3, 4, 5. Okay, so the 5 D orbitals are here. All of them are actually existing in the same energy level. Right now, what will happen is ligands will approach. The moment ligands approach, they will split up. There will be Eg and here there will be T2G. Correct? Yes. Now let's say that we have D1. There is only one electron in the D1 right here. At T2G level, you have only one electron. Now, if this one gets certain level of energy, what will it do? It will get excited to the higher D energy orbital. See, this T2G is also a part of D orbital. The Eg is also a part of D orbital. What is happening? The electron is jumping from D to D. So what do we call it? We call this to be DD transition. What do we call it? We call this to be DD transition, everybody. Is this clear? Is this clear? What is DD transition? Now, there is a complexity here as well. Do you read this line? V5, Cr plus 6, Mn plus 7, there is no unpaired electron. Nothing whatsoever. But what happens is these are still colored ion. And why? There is charge transfer. Now you are going to ask me, ma'am, what is this charge transfer? Please tell us that also. Chal. Let me show you. For example, I was just talking about Cr, right? Cr plus 6. So let me show you here. Check it out, everybody. Yes, let's draw for CrO4. CrO4 2 minus. Yes, it is a deep yellow color. CrO4 2 minus. It's a deep yellow color. Very nice, amazing yellow color it is. Okay. Yes, so in this case, if you calculate the oxidation state, you will find that Cr is in plus 6 state. If Cr is in plus 6 state, then you know that scandium, titanium, vanadium, chromium. Chromium is what? 24, atomic number 24 bole to 3d5, 4s1. So all the 6 electrons are gone. That means it is at 3d0. Now, let's draw the structure and let's try to understand, okay? So, what is the structure going to be? The structure is obviously Cr here, okay? Then you have O here, right? And then you have one O here and then you have one O here, right? Yes. Now, the Cr, this is in plus 6 state, right? But this O has a negative charge here, correct? This O, what it will do is it will transfer this charge here. Yes, this negative charge will get transferred to the plus 6. Cr has a plus 6 positive charge, right? Cr has a plus 6 positive charge. So this negative charge, what it will do is like, oh, let me be the bigger person. I will donate. It will try to transfer it. It's like, lele bhai, take it from me. You don't have anything anyway. You are at 3d0. You take some charge from me. So because of this negative charge, yes, this negative charge which got transferred, the negative charge got transferred. You just saw, right? The negative charge got transferred, and because of that, the color is exhibited. Due to which color was exhibited. Okay. Due to which color was exhibited. Correct? Due to which color was exhibited. And very similarly, now you can also do it for Mn plus 7. Mn plus 7 is MnO4 minus. MnO4 minus will show you what purple color. Why? Because O4 minus, from O negative, it will go to Mn plus 7. And due to this charge transfer, you get to see the colors in transition elements. Alright. So now take a look at it. Everybody. You can see very clearly. Very clearly you can see that, see, the colorless compounds are Sc2 plus 3d0, Ti plus 4 3d0, Zn2 plus 3d10. Fully filled or empty orbitals will always be colorless. No questions, no doubt about it, right? Absolutely correct. Yes. Now see, Ti3 plus 3d1. There is one electron present. Yes, one unpaired electron present. So purple. Blue color, you will see that V4 plus, yes, Cr2 plus, Cu2 plus. These all have at least one unpaired electron and they will all show you blue color. And like that, I will anyway be giving you the PDF which you can read it later. But right now, do you understand how we are getting the color, everybody? Is this clear how we are getting the color, everyone? Yes? Yes, everybody? All done? All set? Chalo. Moving on. Let's take a look at some of the questions. Yes, these have come in JEE Mains 2021, everybody. So take a look at it. The set having ions which are colored and paramagnetic, both are. Colored and paramagnetic, everybody. What do you have to do, my dear students? What do you have to do to figure this out? I mean, you know, right? Do I even have to tell you this? Yes, I think you can solve it. No? Can you not solve it? I think you can solve it, guys. Look at it. Cu2 plus. Cu2 plus will have Cu2 plus. Cu is what? 29. 29. So 3d10, 4s1, 2 plus. That means that it will be 3d9. Correct? It will be 3d9, isn't it? Now Cr3 plus. Cr3 plus will be 4s1 gone and 3d2 gone. So it will be 3d3. Yes. Sc plus will be what? Sc plus will be, everybody, scandium is 21. So 3d1, 4s2. That means that it will be 3d1 and 4s1. Yes. So all of these are going to be colored and paramagnetic. Option 1 is definitely true. Right? See, we just solved it. Everybody. Yes. It's so easy. To you see. Now, as I already told you that yes, the D block elements, they also do form a lot of complex compounds. Yes, they form complex compounds in which the metal ion, it binds to a number of anions or neutral molecules which are called as ligands, and this is something that we have read thoroughly in coordination compound. All of these are coordination compound. Check it out: FeCN6, FeCN6 4 minus CuNH3, 4 2 plus PtCl4 2 minus, all of them are coordination compound. Correct? Yes. Now, why is that the transition metals, they form a large number of complex? Why is it something? Why is this not a property that is shown by S block elements or the P block elements? Well, because comparatively they are of smaller size, right? We know that S block elements are really huge in the size, right? They are actually the biggest in their sizes, and we know that in periodic table when you move from left to right, the size decreases. Correct? So in case of these D block elements, we know that they are comparatively smaller size of the metal ions. Yes, and they are highly ionic because obviously they are showing variable oxidation state, +2 to +7, they can show it all. So they are highly ionic charges. Yes, and they have available d orbitals, they have empty d orbitals to give it to other molecules for bond formation, which is why you get to see such an enormous range of complex. Yes. And now, my dear students, we are here to the most important part of this chapter, and that is that potassium permanganate and potassium dichromate. We have to learn about them. There is no other way we can go about this. Okay, there is no other way that we can go about this. Now, first of all, take a look at the manganate ion. The manganate ion, my dear student, is the green in color, and the permanganate ion is diamagnetic. Permanganate ion is diamagnetic because you know +7, so 3d0, there are no electrons only. So how is it going to show you any how is it going to show you any magnetism? It cannot, right? Whereas this, the green ion, that is MnO4 minus, this will show you some kind of magnetic property because it still does have some unpaired electron, right? Now, manganese 1, manganese in +2 oxidation ion salt is oxidized by peroxide disulfate to form permanganate, which is what we are going to read now. Don't worry about it. Just read the properties once. It forms a dark purple, almost black color crystals. The crystals are isostructural with KCl4. That means that KCl4, what the structure of KCl4 looks exactly like this crystals. Okay, it's not very soluble in water. All right, when heated it decomposes at 513 Kelvin, which is what you will see here. Okay, now we are going to understand the preparation, everybody. So first of all, what we are going to learn is we are going to prepare KMNO4. Okay, we are going to take a look at the preparation, and it is going to be easy, promise. Just check it out. Okay, preparation of KMNO4. Yes, first of all, let's prepare it with pyrolusite ore. Okay, yes, what are we going to prepare it with? Pyrolusite ore. Where will you be reading about pyrolusite ore? In metallurgy chapter, which we will do, don't worry. Okay, now pyrolusite ore is MnO2. All right, yes. From pyrolusite ore, we will be creating potassium manganate. What are we creating? We are creating potassium manganate, not permanganate. Potassium manganate, everybody. Chalo, look at it, 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 look at it. Okay. So what are we taking? We are taking MnO2. MnO2 is our pyrolusite ore, right? So let's take 2MnO2. Yes. And in that, what are we going to add? We are going to add an alkali. Why? Because see, potassium manganate, the name is written here, potassium, we need potassium. Where are we going to get potassium from? Let's take KOH, right? Let's take potassium hydroxide, easy peasy. So we will take KOH, and obviously we will need a little bit of oxygen here, so that now what will we get? We will get K2Mn, yes, O4. And obviously, since there is O2 and since there is hydrogen and since there is oxygen here, so you will get some H2O as well. Now just balance it. Now just balance it. You will be seeing 4 here and you will be seeing 2 here. Okay. All right. Now what are we going to do is, this part, when we are going to put it in a neutral or acidic medium, okay, we will put this in a neutral or acidic medium, everybody, and see what we will get. I'm going to move aside so that you can see the whole board, everybody. I hope that you all can see it, right? If I move away like this, yes. Okay. Chalo. So now what are we going to do? Now we are going to disproportionate it, okay? We are going to disproportionate it in a neutral or acidic medium. Check it out. Proportionates, yes. Disproportionates in acidic or neutral medium. In neutral medium. So first of all, what did we take? We took some base, right? KOH was a base. KOH is obviously a base, right? Now we are going to take it in a acidic or a neutral medium. So what will we get? Check it out. Okay, changing the color, everybody. So from here we will take 3MnO4 minus 2 minus, because see 2K2 we are removing the K2 part. We are removing the K2 part so that we get MnO4 2 minus. All right. Yes. Now what are we going to add? See, acidic medium, it says that means that H plus. Okay. Let's add 4H plus. So what will we get here? We will be getting MnO4 minus. Okay. This H plus is there, right? H plus is there. So we will get MnO4 minus plus. What will we get? MnO4 minus we have found, but there is still another Mn left. So we will be getting MnO2. All right. MnO2. And obviously, finally, we will be getting 2H2O. Makes sense? Disproportionation. That means MnO4 2 minus will be breaking into MnO4 minus and MnO2. Cool hai, everyone? Yes. Now let's take a look at the commercial preparation. What are we taking a look at this time? Let's see commercial preparation. Commercial preparation. How do we prepare it commercially? Again, very easy. What do you have to take? You have to take once again pyrolusite ore. Okay, so let's take pyrolusite ore, that is MnO2. Yes, once we take pyrolusite ore, what are we going to take? Same, very similarly. See, here also we have taken KOH, right? We will do the same thing, but here what we will do is, it's just a little bit different. Just a little bit different. Fused with KOH. This is exactly what is written in your NCERT, by the way. Okay, fused with KOH and oxidized with. And oxidized. See, here also you added oxygen. Here also you added oxygen, right? So oxidized with. This time what you will do is with air or KNO3 or potassium nitrate. Okay. All right. Now what you will get? You will get MnO4. What you will get? What did you get here? MnO4 2 minus, isn't it? So you are getting MnO4 2 minus, which is nothing but the manganate ion. Okay. What is this? This is your manganate ion. Manganate ion. That means that this is the one that is green in color. Okay. Now from the manganate ion, what will you get? You need MnO4 minus. You need permanganate ion. You need MnO4 minus, right? So what will you do? You will go for electrolytic. You will go for electrolytic oxidation. Electrolytic oxidation in alkaline solution. In alkaline solution, and that is how you prepare it. That is how you prepare it commercially. But are we done? No, we are not done. Now we are going to prepare it in laboratory. Okay, where are we preparing? Let's prepare it in lab. And in the laboratory, everybody, do you remember what was written here? See, peroxo disulfate, correct? So let's take the peroxo disulfate. What is this peroxo disulfate? Very easy, very easy. So first of all, we have Mn2 plus, right? We have Mn2 plus plus peroxo disulfate, S2, peroxo, that means that there is an oxygen bond in between, right? Yes, there is an oxygen bond in between, plus or both of these sulfur will have 1 2 3 1 2 3, that means 6, and then there will be 2 oxygen bond in between, so that means O8. Okay, yes, O8 2 minus, obviously, because it is Marshall's acid. H2S2O8 you take. Now if I have removed H2, so what will I get? Peroxo disulfate, S2O8 2 minus. Let's take 5 of this. The moment you see this, plus here you are going to take 8H2O. So what will you get, everybody? What do you want? What do you want? You want permanganate ion. So 2 MnO4 minus, right? The moment you have taken, now see, 5 into 2, 10, right? You're supposed to get 10, isn't it? You're supposed to get 10. Yes, you will be getting that. 10 SO4 2 minus. Everything else remains the same. Okay, 5s2, so 5 2s are 10. You write it, this is how you have to learn. Okay, 10, and then here you have 8 here, so 8 5s are 20, and here you have 4 10s are 40. Okay, so we are not done, we're not done. 8 5s are, no, 8 5s are 40, 4 10s are 40. Yes, 40. It's over. It's over. So all we are left with now is 16h plus. 8 2s are 16. 16h plus. You are left with easy peasy. Easy peasy. And now when you heat it at 513 Kelvin with whatever things you have made it. What are the things that you have made? What are the things that you have made potassium permanganate with? You have taken MnO4 minus, you have taken MnO2, and you have taken oxygen, correct? All of those things will just come out, okay? So whatever I said, I have said that 2 kMnO4, if you heat at 513 Kelvin, what you will get? You will get MnO4, K2MnO4, plus you will get MnO2, plus you will get O2. This is the answer. With whatever you have made it with, these are the things that you will be getting. Okay, these are the things that you will be getting. All right, now I am going to just rub this once again because I have to write something else. Okay, this is already written in the in the slide, and in fact let me show you. Let me show you, everybody. Just a second. Sorry. Yeah, just a second. See, this is what is written. This is already written here, which is why I'm not writing it again. But now I have to write down some more reactions that are there in your NCERT book. So let's do that. Okay. So obviously, what are we taking? We are taking MnO4 minus. Okay, we are taking MnO4 minus, and then we have certain reactions that we have to write. So I am just going to write all of them here. First of all, everybody, first of all, what do you know about iron? What iron, if we take MnO4 minus and if we add some iron to it, what will happen? Let's say that we are taking Fe2 plus. Yes, Fe2 plus, and let's say that we are taking 8H plus. The moment you see 8H plus, write down half of it 4H2O. Yes, there will be 4H2O. Now, do you see 5 Fe2 plus instead of Fe2 plus? You know Fe is in. Fe is in the most stable form. Where? Fe3 plus, isn't it? So, let's just write it down. Fe3 plus. 5 Fe2 plus will become 5 Fe3 plus. But what is remaining, everybody? What is remaining, guys? What is remaining? What is remaining? What is remaining? You will be getting, you will obviously be getting, everybody, Mn2 plus Mn2. Not Mn2 like this. You will be getting, one second. Not Mn2 like this. I think you will be getting, how did I forget this? Wow. I think, yeah, Mn2 plus. Yeah, MnO4 minus, you will be getting Mn2 plus. That's it. Easy peasy. That's it. Right? Got it? Okay. Now let's take another element, that is, let's take iodine. Okay, let's take iodine. This time let's take 10I minus plus. Obviously, how much are we going to take? We are going to take 16H plus. So the moment you see 16, what are you going to write? You write 8H2O. Okay, the moment you write 8H2O, then you see that there is 10I minus, right? So instead of 10I minus, what is it going to be? You tell me that. But before that, let me write down that 2Mn2 plus it is going to be, and then it will be 5I2. 10I minus will get converted to 5I2. Easy peasy, everybody. Are you guys understanding? Are you guys understanding, everyone? Well done. All right, moving on. Now let's take oxalate ion. Okay, let's take oxalate ion. I think these are the examples that are there. 5C2O4 2 minus, isn't it? And once again, we are going to take 16H plus. The moment you say 16H plus, what should be? What should come to your mind? 8H2O plus. What will you be getting? You will be getting here 2Mn2 plus. Yes, 2Mn2 plus. And what will you be getting? See, 5C2O4 2 minus. That means that 10CO2. Easy peasy, everybody. Are you all able to learn it with me? All right. Next, everybody, let's take H2S. Okay, let's take H2S. How many H2S do we take? Let's take H2S. Chalo, H2S. But this H2S will do what? It will become 2H plus S2 minus, right? So from here we will take 5S2 minus. Okay, 5S2 minus plus 16H plus, let's take. Okay, 16H plus. So the moment, once again, you're seeing 16H plus, that means 8H2O, write it down, plus what will you write? 2Mn2 plus, alright, 2Mn2 plus, and now that you have taken 5S2 minus, that will obviously become 5S. Easy peasy. Are you all able to learn it? Learn it right away, everybody. Learn it right away. Now what are we going to take? Let's take sulfurous acid to sulfuric acid. Okay. We want to take sulfurous acid, that is SO3 2 minus 5. Let's take. Okay. Plus what you will do is 6H plus. You take 6H plus. The moment you see 6H plus, what should come to your mind? It will be half of it. That means 3H2O. 3H2O plus 5SO4 2 minus plus 2Mn2 plus. So Mn2 plus, Mn2 plus, Mn2 plus is common everywhere. Can you see it, everyone? I believe that you are able to learn it. Last one, everyone. The last one is nitrite to nitrate. Okay. What are we doing? Nitrite to nitrate. So 5NO2. NO2 minus, yes, plus what are we taking? We are taking 6H plus, 6H plus, that means that obviously 3H2O plus 2Mn2 plus NO2 minus, yes, instead of NO2 minus, what do we need? We need 5NO3 minus. And that's it, my dear students. That's it. That's it. This is, by the way, in the acidic nature. Yes, where was this? This is in the acidic nature. Now we also must do it for the basic nature. Okay, not basic, neutral or alkaline. Okay, let's do it for neutral or alkaline. But neutral or alkaline, I'm so sorry, by mistake I wiped it all off, but let me write it down again so that everybody, all of us are on the same page and we can understand. Okay, so once again, everybody, as I said, that we are taking a neutral or alkaline medium. Yes, neutral or alkaline medium. Yes, this is what we are taking. Now that we take this, what are we going to do? Now that we are taking this, what are we going to do? Check it out here. Obviously, once again, we have MnO4 minus that we are taking, and from here we have to convert iodide to iodate. Okay, we have to convert iodide to iodate. So MnO4 we are taking, but let's take 2 MnO4 minus plus iodide, right? Iodide, that means I minus plus, see, neutral or alkaline medium, right? So let's just take H2O. Now that we have H2O, we just have to write what? We have to write 2OH minus, okay? Plus, what are you going to get? 2MnO4 minus, 2MnO4 minus, that means that it will become 2MnO2. Yes, it will become 2MnO2. And plus, you will be getting IO3 minus. Okay, this is your reaction. Easy peasy, everybody. Next, what are we going to do? Next, let's take 8MnO4 minus, obviously H2O we will take, and let's take 3S2O3 2 minus. Okay, now the moment you see this, what will you make? You will be making 8MnO2 plus 2OH minus plus, do you see 3S2O3? So instead of 3S2O3, 3 2s are 6, that means 6SO4 2 minus. This is your answer, everybody. This, my dear student, is where you end your potassium permanganate. Okay, now what do we have to learn? Now we have to learn about potassium dichromate, but before that, let's do one or two questions. Why not? I mean, obviously we are solving questions here, right? Only then we will be able to get to our dream college, that is IITs. Chalo. Potassium permanganate on heating at 513 Kelvin gives a product which is, everybody, you have seen it, right? You have seen it. Check it out. MnO2, no, not this here. See, 2KMnO4, when you heat it at 513 Kelvin, what are you getting? You are getting K2MnO4 plus MnO2 plus O2. That means that you are going to get a green color ion which is paramagnetic in nature, right? That means option D is the correct answer, everybody. Easy peasy. Yes, option D is the correct answer. Next question. The Eu2 plus ion is a strong reducing agent in spite of its ground state electronic configuration. Okay, this we are talking about lanthanoid. So how about, I'm going to give this to you as homework, or what we can do is we can come and revisit this question later once we are done with the F block. Since I have not taught you F block yet, I can do the answer, but you will be confused. So we will either revisit or I'm giving it to you as a homework. Okay, we will see what we can do. Chalo. Moving on from here, there is another question. Okay, this we will be able to do. Potassium permanganate on heating at 573 Kelvin forms potassium manganate. Okay. Both potassium permanganate and potassium manganate are tetrahedral and paramagnetic in nature. Okay. In the light of the above statement, choose the most appropriate answer from the options given below. What do you think? Potassium permanganate on heating at 573 Kelvin forms potassium manganate. That does seem right? Yes. Both potassium permanganate and potassium manganate are tetrahedral and paramagnetic in nature. Yes, the correct answer is option B. Because see, statement 2 are paramagnetic in nature. No, Baba, both of them are not paramagnetic in nature. Only manganate ion is paramagnetic, but the permanganate has what? +7 oxidation state, and +7 oxidation state, as we know, cannot be paramagnetic because what? D0, bacha, no electron are there. No electron are there. How will it show magnetic nature, right? So option B is the correct answer here. Okay. Now, in a mildly alkaline medium, thiosulfate ion is oxidized by MnO4 minus 2A. The oxidation state of sulfur in A is. Can you tell me? See, what is the question? Thiosulfate ion is oxidized by MnO4 minus. Basically, we are talking about this reaction. Okay, we are talking about this reaction. In this reaction, can you find out 6SO4 2 minus? What is the oxidation state? I think you should be able to do this. Yes, you have by now you have learned how to find out oxidation state, and we have found out the oxidation state of many elements. What is the correct answer? Yes, you just have to do it. Yes. You just have to calculate, guys. The answer is given here. The answer is given here. Please calculate it on your own. Giving it to you this as also homework. Okay. This is also homework. You know what? I'm just a little too much pain is happening. So I'm trying to cover this chapter a little faster. So the question is for you. Homework. Take this as a homework. Chalo. Moving on to the next question, everyone. Now we come to potassium dichromate. Okay, so what is potassium dichromate? There is a lot of text that is written here. Let's not read all of these right now. What we are going to do is, you will be able to read this on your own, read it on your own, but right now we're going to talk about the preparation of potassium dichromate. Ready, everybody? Yes. What are we going to talk about? Let's talk about preparation of potassium dichromate. Preparation of potassium dichromate. All right, dichromate. How do we prepare it, everybody? How do we prepare it? Where do we prepare it? In the lab, in the commercially, where do we prepare it? Anyway, forget about all of these questions. First of all, let's try and prepare it. How do we prepare it? We are going to take chromite ore, and that is what is written here. See, the fusion of chromite ore. What is chromite ore? FeCr2O4. That is your chromite ore. Okay, so we are going to take chromite ore, which we have just found out that it is FeCr2O4. Okay, all right. Yes. Now let's write down the reaction FeCr2O4 plus what we are going to do is, see, that is also written here. It is written that you are going to take this with sodium carbonate. So let's take sodium carbonate. Sodium carbonate is what? Na2CO3. Na2CO3, right? Na2CO3. Okay. Now see what will happen is, okay. Now see what will happen. This Na, and imagine, don't you think that this you have seen somewhere, Cr2O4, oxalic acid, somewhere like this. Does it look like this? Does it look like this? Cr2O4, basically kind of like, you know, it looks like an acidic form, isn't it? Acidic form, yes. And then here you have Na. Okay, so what will happen is, you will see that NaCr2O4. This is what you will get. Na2Cr2O4, and because there is 8 here, let's write 8 here as well. Okay, all right. Yes. Now what is remaining? You have F here, you have CO3 here, right? So that means that we can write Fe2O3, obviously. And carbon dioxide, because there are so many C. So carbon dioxide, everybody. Makes sense? Easy peasy. Makes sense? Now this, my dear student, this is your chromate. Okay, this is your chromate. But what do we need? We need dichromate. From chromate we need dichromate. How do we do it? We will take here 2Na2Cr2O4 plus, let's acidify it. Okay, let's acidify it. Okay, so let's acidify it. How do we acidify? We can either take H2SO4, or let me just write here H plus ions. H plus ions means that we are acidifying it. Now what will happen is, we will be getting, okay, did I write Cr2O4 everywhere? No. That's not gonna happen. Sorry. CrO4. That's why this is chromate. This is chromate. NaCr, Na2CrO4. Yes. Now after acidifying, what will we get is we will be getting Na2Cr2O4. Okay. This time we are getting dichromate. Previously it was chromate. There was just one chromate. Okay. There was just one chromate, everybody. Alright. Yes. So this is your dichromate. After that, what will you get here? After that, what will we get you? What will we get you? Yes. Na2 here, but there are more and Na plus ions left. So Na plus ions left. Yes. 2 Na plus ion. And plus what will you get? Since H plus is there, so obviously some amount of H2O as well. Okay. Now, do you see that you still have sodium dichromate, everybody? You still have sodium dichromate. But do we need sodium dichromate? No, we want potassium dichromate. So what do we add here? Easy peasy. Just add some potassium salt, right? So what will we do here is we will be taking Na2Cr2O4 plus let's just add KCl so that we get some salt. So we will get K2Cr2O7. Okay. All right. Plus what will we get? Plus we will get NaCl. Obvio. I mean, come on. Is that even a question? Is that even a question? There is no question about it, right? So is this clear, everybody? Now check it out what is written here. Okay. Now you can see the fusion of chromite ore with sodium or potassium carbonate in free access of air products. What will you be getting? You will be getting sodium chromate. Once you get sodium chromate, you acidify it, you will be getting sodium dichromate. Once you get sodium dichromate, you just have to add a potassium salt so that you get the sodium salt outside and potassium attaches itself with the dichromate and you get potassium dichromate. Everybody, is this clear, my dear students? Yes, is this clear? Got it, everybody? This is clear, easy peasy, great, amazing. Now, did you know that the chromate and the dichromate, they are interconvertible in aqueous solution? Yes, absolutely yes. Okay. The chromate and the dichromate ion, they are interconvertible in the aqueous solution. What will happen if you acidify it? You will be getting dichromate ion. If you just add some alkaline to it, you will get the chromate ion. Okay, that is exactly what is written here. That is exactly what is written here. All right, everybody. Yes, this is clear. Now we do need a little bit of more space. So what I'm going to do is I'm just going to add a little bit more space here. Okay. All right. Where are we? We are here. Now from here, I'm going to add another slide, and now let's yeah. I have to write a little bit more because we know that this is a strong oxidizing agent. Okay, this is a strong oxidizing agent. So obviously this also has its own reaction, just like how we spoke about the potassium permanganate. This also has its own reaction. So let's do it, everybody. We are going to take Cr2O7 2 minus plus. Let's take some acidic. Yes, let's take some acidifying something H plus. Let's just take H plus. All right. Yes. Now what are we going to do? What are we going to do? We are going to take 6I minus. 6I minus. The moment you say 6I minus, what will you be getting? You will be getting 3I2. Yes. Plus 6 electron here. Write that down. Now let's take H2S. Yes. How many H2S? Let's take 3 H2S. If we take 3 H2S, what will we get? 3S plus 6H plus and plus 6 electron, obviously. Correct. Next, what do we take? Obviously, let's take 3Fe2 plus. Why am I writing like this? Why am I writing like this? No idea. Let's take 3Fe2 plus. If we take 3Fe2 plus, we know that Fe2 plus is not the stable form. What will we get? We will be getting 3Fe3 plus. And what will we get? What are we doing? What am I doing here? Let's take 6Fe2 plus. If we take 6Fe2 plus, what will we be getting? What will we get? We will be getting 6Fe3 plus 6 electron. All right. Next, what shall we take? Let's take 6Sn2 plus. Okay. If we take Sn2 plus, then we will be getting 3Sn4 plus 6 electron, and that, my dear student, is your end of potassium dichromate. Okay, this is how we end potassium dichromate. Now shall we do some questions? Shall on treating a compound with warm dilute H2SO4. Okay, let's solve this question. Yeah, so on treating a compound with warm dilute H2SO4 gas, H2SO4, gas X is evolved, which turns K2Cr2O7 solution acidified with dilute H2SO4 to a green compound Y. Okay, green compound Y. X and Y respectively are. Okay, this is very easy, very simple. What we have to do is basically check it out. On treating a compound with warm dilute H2SO4, gas X is evolved. What is the gas X? The gas X obviously will be SO2. Yes, SO2 plus dilute H2SO4, when you add, what do you get? You get SO3 gas. You get SO3 gas. Alright, you get SO3 gas. Correct. Now, if you take this SO3 plus if you add K2Cr2O7, it's written here, K2Cr2O7, what will you get? What will you get? Again, this is also in the acidified solution, right? So this also here will have H2SO4. Now, when you add here H2SO4, what are you going to get? Okay, this you can just balance it, guys. Just balance it. What will you get? You will get Cr2. Yes, SO4, right? Cr2SO4, 3. That's it. So that means that option A is the correct answer, isn't it? Option A is the correct answer. Makes sense, everybody? Chalo, let me move away so that you can see it, what I have written. My goodness, I think that the pain in my back has now traveled to my brain. That is why such wrong English I'm speaking. But yes, I hope that you understood this. Okay, chalo, moving on to the next question. In the structure of the dichromate ion, there is a what structure? How do we write the structure of dichromate ion? You write it like this. You write it like this. Cr, double bond O here, double bond O here, one O here, then you have one O here with lone pair like this. Then you write Cr here, double bond O here, double bond O here, and O minus. What is this? This is non-linear, isn't it? This is non-linear, so it will be non-linear CrOCr, but it is symmetrical. Non-linear but similar, isn't it? Yes, so let's write that option B is the correct answer, which is true. Option B is the correct answer. And now, my dear student, oh, finally we have come to the F block, and I think that we will be able to finish our journey of this chapter right almost in about like next half an hour we will be able to finish it. Okay, so the F block elements, as you all know, that there are two series of F block elements. What do you have? You have the one that is inside the 4D series, and one that is inside the 5D series, and the one that is inside the 6D series. That means that you have two. There is lanthanoids and there is actinoids. The lanthanoids are called as the 4F series and the actinoids are called as the 5F series. And each one of these series, there are 14 elements. Okay. Alright. After lanthanum, there are 14 elements that are present in these ones. Okay. So how do we write how do we remember this? How do we try and remember this? Because there are so many elements, 14 elements, we must remember this. Okay, so write it down. For lanthanoids, okay, lanthanoids, I'm telling you a mnemonic here. This might sound very funny, yes, but please bear with me. Yes, the mnemonic is last century presented new democratic prime minister on social media. Prime minister, or you can also write PM. Prime minister on social media, which is Samarium. Yes, Samarium. But European government had TB and diarrhea. in hotel entirely to make yellow building luxurious. Alright, this is how you remember it. Last century presented new democratic prime minister, new democratic PM. Okay, last century presented new democratic PM on social media, but European government had TB and diarrhea in hotel entirely to make yellow buildings luxurious. I know it sounds a little yucky, but this is the funniest that I could find in English. Otherwise, yes, in Hindi there are many of them, but you know what happens, right? So let's just write it down, everybody. As you can see, last century, the first one right here is your lanthanum. Yes, is your lanthanum. Then you have cerium here. Then you have what? Then you have plasmodium, that is PR. Then you have ND. Then you have PM. Then you have samarium. Then you have europium. Then you have gadolinium. Then you have terbium, TB. Then you have dysprosium. So DY, I think. Yes, you have DY. Yes. Then you have holmium, so HO. And then you have entirely, so ER. There is nothing, huh? TM is also there, so TM. Then you have ytterbium, and then finally you have lutetium. All right, so these are your all the elements that you have. All right, can you all remember this? Last century presented new democratic PM on social media, but European government had TB and diarrhea entirely to make yellow buildings luxurious. All right, everybody. Yes, guys, cool, got it. Now let's take a look at the electronic configuration of all of them, and in this case, if you really take a look at it, you will find that the exceptional electronic configuration are obviously cerium right here. Do you see cerium has 4f1, 5d1 and 6s2? Okay, all right, 4f1, 5d1 and 6s2. Then you have gadolinium. Gadolinium also has 4f7, 5d1 and 6s2. Apart from that, you will also find lutetium. Lutetium also has 4f14, 5d1 and 6s2. These are the only elements which also has a d orbitals. There are some electrons that are present in the d orbitals. Otherwise, in none of the other elements you will find d orbitals, that is filled. Now this is a chart that you just have to look at it and you just have to know. Okay, you just have to know, because you are also getting to see the ionic forms, that is Ln2 plus, Ln3 plus. These are the things that you are getting to see. Ln4 plus. Okay, these are the things that you are able to see in this chart. Now it is just good to know. You will be getting the PDF, so don't worry about it. Okay, all right. Now in this lanthanoid in this topic, when we are talking about lanthanoids, we come across something called as lanthanoid contraction. Okay, where do we see lanthanoid contraction, everybody? I will show you where is lanthanoid contraction as well, but I think it is coming up a little later. Chalo, no problem, let me teach you what is lanthanoid contraction right now. Okay, all right, so what is the cause of lanthanoid contraction? Let's write that down. Okay, the cause of lanthanoid contraction. What is the cause of lanthanoid contraction? Now, if you, like, for example, I have this house, right? In my house, obviously, you put up curtains, right? You don't make a glass house, correct? You have walls, you have curtains. Why? Because you want to keep your privacy with you at any cost, right? You don't want your, whatever is happening in your house, you don't want everybody, the whole neighbor, the whole gully, mohalla, everybody to talk about your privacy, correct? Nobody wants to do that. But that is the case only with s orbital. Now p orbital, you know, in p orbital, what p orbitals do is they have like one or two windows where there are no curtains. Yeah. Then comes f orbital. F orbital, what they do is they keep their door also open all the time, and there are curtains which are not present. Now f orbitals, what they do is every curtain that is there in the whole house, all the curtains are torn. So that means that you can easily see what is happening inside the house. Yeah, that means that f orbitals have the worst kind of shielding. For example, right now if I do this, see, I am shielding my face, right? I'm shielding my face, correct? Everybody, I am shielding my face. Imagine now p orbital. In p orbital, see, now you can see my face a little bit. In d orbital, it's like this. In f orbital, it's like this. This is the shielding. So basically what I'm trying to say is, in case of f orbital, yeah, my hand is right in front of my face even now. You cannot really absolutely see my face. There are parts and features of my face that I'm still trying to cover, but it is very bad. The shielding is really bad, isn't it? So that means that what I'm trying to say here, my dear students, everybody, is that due to poor shielding effect of f orbitals, okay, due to poor shielding effect by the 4f orbitals, you get to see lanthanoid contraction. What is lanthanoid contraction? Once again, everybody, do you remember that we expect the atomic radii to, constantly, what? Constantly decrease a little by little as we move from left to right. All of these 4f orbit, all of these 4f series, all the elements that are there in the 4f series, if you remember, starting of the session I told you that they all belong to group 3. Yes, I know, when you look at the periodic table you might think that no ma'am, how is that possible, they all belong to different groups. No, like I said, if the prime minister, that is lanthanum, if the lanthanum is the leader and lanthanum only belongs to group 3, all the other elements, they also belong to group 3. Okay, all right everybody. Yes, and all of them have very poor shielding effect by 4f orbitals, which is why what we actually see is that there is a constant decrease in the size, and the size decreases very nicely. You can actually see, I will show you the graph is there somewhere, I'll show it to you in some time. I'll show it to you. We will be solving some questions as well, and as we move on, you will be able to see that yes, there is a constant decrease and it decreases very much. So you will not find that you will find that most of the elements, they all exist together of this. Yes, the lanthanoids, they all exist almost together in nature. It's very hard to separate them, and that, my dear student, is the consequence. Okay, so let's write that down also. What is the consequence of lanthanoid contraction? Let's write that as well. Okay, consequence of lanthanoid contraction. Consequence of lanthanoid contraction is, first of all, what you see in periodic table is that zirconium and hafnium, molybdenum, no, not molybdenum, yeah, molybdenum and tantalum, no, niobium, yes, it is niobium and tantalum. Okay, not molybdenum, niobium and tantalum, all right, and molybdenum and tungsten. Yes, they all have almost same atomic size, have almost same atomic size. Cool. Yes, they have almost same atomic size. Lanthanoids are found together in nature. This is what I just told you, right? Lanthanoids are found together in nature, and it is very hard to separate them, and it is very hard to separate them. Cool. All right. Yes. Now lanthanoids, if you look at their oxidation state, what will you find? You will find that the most common oxidation state that they show is a +3. Yes, the lanthanoids, the most common oxidation state, let me write that down. The most common oxidation state, showed by lanthanoids is +3. All right. Yes, but obviously exceptions are always there, right? Now what are the exceptions, everybody? You will be saying that if there is F0, that means empty F orbital. Yes, empty F orbital. When do you see empty F orbital? For cerium and terbium, you will get to see empty F orbital. No, actually for terbium, you will get to see F7, that is half-filled orbital. But for cerium, you will be seeing empty orbital. When do you see empty orbital, guys? Let me show you. For cerium, where is cerium? See, at Ln +4, that means +4 oxidation state. Whenever cerium shows +4 oxidation state, you have to know that cerium will have empty F orbital. Do you see, everybody? Do you see that cerium has 4F0? Alright. Now it is a very strong oxidant and it reverts to cerium plus 3. What it does is it takes one electron and it reverts to plus 3 and it can oxidize even water. But that reaction is very slow, which is why we also like to say that it is a good analytical reagent. Okay, what did I say, everybody? Let me just put all of that in the words, alright, so that you understand what I'm saying. I said that Ce plus 4 will show you empty f orbital. Okay, it is a strong oxidizing, strong oxidant, all right, and reverts to Ce plus 3, all right, reverts to Ce plus 3 and can oxidize water, all right, but that reaction is very slow, hence we just like to call it as analytical reagent. We like to call it as good analytical reagent. Now we come to F7, that is half filled. F orbital. Where do we get to see it? We get to see it in terbium, everybody. Take a look at it. Take a look at it, everybody. See 4f7 at Ln plus 4. That means when there are 4 electrons that are taken away, you will get to see half filled stability here. Yes, half filled stability here. So Tb plus 4 has half filled, F orbital, and this is also an oxidant, and it is an oxidant. Cool, guys? All right. And obviously you will also see fully filled. When do you see fully filled, everybody? When do you see fully filled? F14, fully filled. You get to see fully filled in ytterbium. Ytterbium plus 2 will show you fully filled. Okay, Yb plus 2 will show you fully filled. Now apart from this, do you think that there are other electrons or there are other elements as well which will show you plus 4 oxidation? Yes, you will see that plasmodium, Pr, then you have Nd. Nd is where is Nd? Nd is neodymium. Yes, see praseodymium, neodymium, then you will see that terbium and dysprosium. Yes, these are the ones. Nd, then Tb and dysprosium. Yes, they will show plus 4 oxidation state, but not in aqueous solution. They will only show plus 4 oxidation state in the oxide form of MO2. Okay, in MO2 oxide form, you will get to see that they show you plus 4 oxidation state. Okay. Now, if we have to talk about the ionization energy of lanthanoids, what do we have to talk about? Yes, what do we say? The lanthanoids, their first ionization enthalpy. We are talking about ionization enthalpies, my dear student. That means that IE, everybody knows that, right? Number 1, the first ionization enthalpy is about the first IE. The first IE is comparatively low, so you will see that it is around 1200 kilojoule. Do you have to remember the number? Not really, but if you want to, you can remember. Okay, kilojoule per mole you will see. The second ionization enthalpy, everybody, the second ionization enthalpy is about no, sorry. The first one is about 600 kilojoule. That's what I was thinking, that how is 1200 kilojoule so small? The first ionization enthalpy is comparatively very low. So you will see that it is 600 kilojoule per mole. Second ionization energy, you will see around 1200 kilojoule per mole. Yes, and the third ionization energy is usually exceptionally low for lanthanum, gadolinium and lutetium. Okay, let's write that down. This is exceptionally low. Third IE, exceptionally low for La, gadolinium, Gd and lutetium. This is something that you have to know, okay? Because from here questions might come, all right? From here questions might come, because what they do is they attain the noble gas configuration, right? Here what happens is they attain noble gas configuration because the moment they lose the third electron, what they attain is they attain noble gas configuration. They attain noble gas configuration. Cool, everybody? All right. Now, if we have to talk about the physical properties of lanthanoids, what do we see? Physical properties, we will not take too much time. Physical properties, I'm just going to tell you, everybody. Physical properties, you will see that they are silvery white in appearance. Okay, silvery white in appearance. Silvery white in appearance. Second, you will see that they tarnish very quickly. They tarnish in air. Tarnish means they become black in color. Okay, tarnish in air quickly. All right. Thirdly, obviously they are good conductors. Obviously they are, because they are metals, right? They are good conductors, everybody. Apart from that, number 4, what can you write? Melting point is about, melting point, we can write melting point is about 1000 to 1200 kilojoule. All right. But samarium, there is one called as samarium. Samarium has exceptionally high samarium. Samarium has 1623 kilojoule. Samarium has 1623. Okay, all of them are hard. All of them are hard, but samarium is again steel hard. Okay, samarium is steel hard. It is very hard. Samarium is one of the hardest metal out of all these F block elements. All right, out of all of these basically lanthanoids. Yes. Now, when we talk about colors, do they exhibit colors? Yes, everybody, they do. They also do exhibit colors, and you will see that wherever there are no electrons like La plus 3 or lutetium plus 3, they are colorless. But if we talk about plasmodium plus, okay, let's come back to this, okay. Let's come back to this. Yes, if you see that praseodymium plus 3, see there are 4 F2 electrons, right? This will show you what color, do you know? This will show you green color. This will show you green color. And can I tell you something? Just like praseodymium here, you will also see that thulium. Thulium at 4F12 will also show you green color. Thulium will also show you green color. Yes. Again, I'm gonna show you a connection here. Okay, I'm going to show you a connection here. Now see, neodymium will show you. Neodymium has 4F3, right? Do you know what color this will show? Do you know what color this will show? This will show you, my dear students, this will show you, what color does it show? Pink. Pink. Yes, it shows you pink. This will show you pink color. Now, just like neodymium, what you will see is erbium. Erbium will also show you pink color. All right, erbium will also show you pink color. Then we come to samarium. Samarium will show you yellow color, everybody. Okay, samarium will show you yellow color. And just like this, you will see that holmium, no, dysprosium. Dysprosium will also show you yellow color. All right. So like that, that means that here we have found a, link here. What is the link? The link is that, NF electrons, if there are NF electrons, and if there are 14 minus NF electrons, if it is same, see 4F2 and 4F12. Now 14 minus 12 is what? 2. So that will also show you the same color. You got it? Yes, this is for color. This is for color. This is for color. Same color will be seen here. Understood, everybody? Yes, with this note, color is also done. Now, can we go to their uses? Yes, what are the uses? Let's talk about the uses also. Where are these metals used? They are used in something called as mish metal. There is something called as mish metal, which you will find in your NCERT as well. Mish metal basically has 95% lanthanoids and 5% iron. 5% iron and some traces of carbon and sulfur, and some traces of carbon, sulfur, etc. Okay. All right. It is used in petroleum cracking. Like once you get from petroleum, you get many products, right? So you have to break it down. You don't get everything as it is, right? So it is used in petroleum cracking. Apart from that, with manganese, was it? Manganese, magnesium, what is magnesium? Yes, magnesium based alloy. Magnesium based alloy is used for bullets. Magnesium based alloy to make bullets. All right. Yes. Then individual oxides. Okay. If you have individual oxides are used in the fluorescent TVs. Oxides are used as phosphors. are used as phosphors. All right. And finally, one last was there that mixed oxides. Mixed oxides are only used in petroleum cracking. Mixed oxides. Here you write mixed oxides. Mixed oxides are used in petroleum cracking, whereas individual oxides are used in phosphors. All right. Now we go to actinoids, my dear students, and we are almost done, everybody. So the actinoids are usually, they are not usually, most of them are radioactive elements, and they have half-life decreasing as we move towards the right. From left to right, when you move, what you see that the half-life is decreasing, decreasing, decreasing. That means they stay for a very less time. Okay. Now, what is the way to learn the actinoids? Chalo, let me tell you that also. This is fun. This is also fun. So write it down. Thor, everybody. You all are fans of Avengers. Everyone knows who is Thor, right? So Thor protected, you write. Thor protected Uranus, Neptune, Pluto, and America came back to California, but we see that Einstein, Fermi, Mendeleev are Nobel laureates. Isn't that sad? Thor saved all of these countries, but he did not get anything. It was Einstein and Fermi and Mendeleev who got the Nobel Prize. So let's write, what do you have? You have thorium here, you have protactinium here, you have uranium here, you have neptunium here, you have plutonium here, then you have americium here, then you have, I have forgotten, then you have curium. Then you have curium here, then you have berkelium here. Yes, no, berkelium is Bk. Then you have berkelium here. Okay. Then 2 is nothing. Then you have californium, that is Cf. Okay. Then but is nothing. Then you have Es, that is Einsteinium. Then you have fermium, so Fm. Then you have mendelevium, so Md. R is nothing, then you have Nb, and then finally you have lawrencium. So Lw, this is not No, this is No, nobelium. Okay. All right, everybody. So now just take a look at all the names. You have actinium, thorium, protactinium. Yes, protactinium is Pa. Did I write Pr? Pa. Yes, Pa. Yes, then you have uranium, then you have, where is neptunium? Np, then you have plutonium, then you have americium, then you have curium, then you have berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. All righty. Yes. Now, what is their general electronic configuration? Obviously, we will have to talk about this. Let's write about their general electronic configuration. General electronic configuration. What is the general electronic configuration, my dear student? The general electronic configuration, everybody, as you all will see, it is 5F1214, yes, 6D021, and it is 7S2. Now, you will see that these two are variable occupancy. Yes, not always you will find that electrons are occupying these two orbitals, but sometimes they are and sometimes they are not. So this is called as variable occupancy. You will not find that always they are existing. Check it out, everybody. Check it out. Yes, see 6D is here, but 6D is also in thorium. 6D is in protactinium, uranium, neptunium, but it is not there in plutonium, americium, and plutonium, americium. It's not there. So do you see what I was talking about? Yes, do you see what I was talking about? This is it. This is it, everybody. Okay. All right. Now here are some questions. And that's it. About actinoids, we don't study more. We are almost right here at the end of it. Now let's do some questions. So tell me what I was telling you right now. The question is that number of electrons present in 4f orbital of holmium HO3 plus ion. You just read it. HO3 plus. Where is HO3 plus? HO3 plus here. See, HO3 plus is how many? 4F10. So what do we write? We write 10 electrons. Correct? Yes. What do we write? We write 10 electrons. Correct, everybody? Yes. I'm pretty sure that you are not able to see this, right? You're not able to see the blue color, are you? I don't think so. Alright, chalo, let me write that down here. 10 electrons. 10 electrons are present, guys. Okay. Moving on. Now, the number of 4f electrons in the ground state electronic configuration of GD2 plus. How much is there? How many are there? Chalo, check it out, everybody. GD2 plus we are talking about. Yes, GD2 plus is gadolinium. Gadolinium will be here. Check it out. GD2 plus have 4f7. So that means that what do we write? We will write here 7 electrons, everybody. We will write here 7 electrons. Got my point? Yes. Next question, everyone. The number of F electrons in the ground state electronic configuration of NP. NP is Neptunium. Yes, NP is Neptunium. Neptunium, we check it out. How many do we have? How many do we have for Neptunium? Here we have ground state. So 4, 1, 5, 4 plus 1, 5, 6, 7. Neptunium. Neptunium will have ground state. What is the question once again? Let's read it. Z is equal to 93. Number of F electrons. Number of F electrons in the ground state electronic configuration. Why does it say 18? Number of F electrons in the ground state electronic configuration of NP. Ground state NP. 5F4 only it is. 5F4 it is supposed to be. Why is it 18? Let me check this. Let me check this out. Why are they saying that the number of F electrons? How can it be? This seems a little wrong, no? Chalo, let's take a look at the other one. So this is what we were talking about when I said that atomic and ionic size. Remember that I told you that we will take a look at the lanthanoid contraction, and this is how the lanthanoid contraction looks like, everybody. See, you see that there is a steady decrease, right? There is a gradual decrease and it just basically gets to a very small. Lutetium has a very small, right? As you see that it just is decreasing. All right, it is just completely decreasing again and again. If you want, you can look at the graph more carefully. Then we go to lanthanide's reaction. This is the last bit of it, everybody. Almost there, guys. Almost there. We're ending it. Almost close to it. Okay. We will come back to that question. Don't worry about it. I will get back to the question. Yes, everybody. Very soon, but like I'm asking you to look at it. So here you will see that lanthanoids, yes, lanthanides, what they do is, if they react with halogens, okay, if they react with halogens, you will see that it gives you LNX3. That means lanthanum with any other halogen, it will form a trihalide. What does it form? It forms a trihalide, okay? It forms a trihalide, everybody. Moving on with H2O, you will see that it forms a hydroxide and it will give you hydrogen gas, okay? It will give you hydrogen gas, everybody, okay? Then you see that lanthanides with carbon it will give you C2, LnC2. With nitrogen also it reacts and it forms Ln capital N. With sulfur, when you heat it with sulfur, it forms Ln2S3, and when it bonds with oxygen, you get Ln2O3. Okay, it comes back to Ln2O3, everybody. Understanding? Yes, everyone. Is this clear, guys? Is this clear? All right. Chalo, moving on, everybody. Moving on. Let's just get back to that question, which I think this is absolutely not making any sense, and it will be. Oh, now I get it. What they're saying. Now I get it. So it is 93 here, right? If it is 93, chalo, for Neptunium, let's write down the configuration. Okay, let's write down the configuration. 93, right? 1s2. 2s2, 2p6, 3s2, 3p6, 4s2, right? Then it will be 3d10, correct? Then 4p6, yes. Then it will be 5s2, right? 4d10, everybody, right? 5p6 and 6s2, 5p6, then 6s2. Then we will have 4f14. That's why. That's why. Because Neptunium is in the 5F series, guys. That's why I got confused. Oh, it is 4F14. Then what will we have? We will have 5D10. Then we will have 6P6, 7S2, 5F4, 5F4 and 6D1, which is why I got confused. So 5F4 plus 4F14, there will be 18 electrons, my dear student. That is why 18 electrons. Got it? All right, guys. Moving on from here, next question is, next question, everybody take a look at it. Next question is, which one of the following lanthanoids does not form MO2? For MO2, we only spoke about 4 of them, right? Ytterbium will not form MO2. Okay. Option C is the correct answer. Ytterbium will not form MO2. Okay. These are the oxidation state. Once again, they have variable oxidation state, but the most common that you see is +3, +3, +3, +3, +3 across everywhere. Okay, you will see +3 across everywhere. That is the most common oxidation state. But neptunium and plutonium, they do show +7 oxidation states as well. Okay. Next question. Which one of the following lanthanides exhibits +2 oxidation state with diamagnetic nature? Diamagnetic means either there should be 0 or it has to be fully filled. And we again know that ytterbium at +2 oxidation state will show you 4F14, right? There will be 14 electron, which is why ytterbium will be diamagnetic in nature. And I think this is the last question, everybody. Tell me. Assertion A. Size of Bk3 plus berkelium ion is less than Np3 plus ion. This is true. Obviously, right? Thor saved berkelium ion is less than, yes, because of actinoid contraction. There, just like lanthanoid contraction, there is also actinoid contraction. The above is a consequence of the lanthanoid contraction. No, I just said that this is actinoid contraction. So option B is the correct answer. A is true, but R is false, my dear students. And finally, I think we are done with the session. With this note, everybody, I hope that you found this video beneficial for you. If you did, don't forget to share it with your friends, and I'll see you very, very, very soon. Stay tuned to the channel. All the very best. We are trying to do as much as we can. I'll see you very, very soon. All the very best, and bye.